Hello there, and welcome to Just About Earth, where curiosity slows down, explanations take their time, and science is something you can listen to at the end of the day without feeling rushed. Tonight, we're going to settle into a story that begins quietly, in a world of melting ice and slow-moving water, and then unfolds into one of the most powerful floods our planet has ever known. It starts, as many of Earth's great stories do, with something that seems calm on the surface. Imagine a lake so large that standing on one shore, you would never see the other. A lake so wide that, from above, it looked less like an inland body of water and more like a pale inland sea, stretching across the heart of a continent. Its edges shifted with the seasons. Its shoreline crept forward and backward year by year, and for a long time it simply existed there, quiet and immense, held in place by walls of ice. Eventually that quiet ended, but we won't rush ahead to that moment just yet because the setting matters, and like any good story told slowly, it helps to begin by getting comfortable and looking around. Before we go further, I'd like to ask you something gentle and simple. Where are you listening from tonight? Are you in a quiet room, already wrapped in blankets? Maybe you're listening through headphones, the outside world dimmed a little, the day settling behind you. And what time is it where you are right now? Late evening perhaps, or already well past midnight? It's always a curious thing to think about, how people scattered across different places can share the same story at entirely different hours, each of us in our own small pocket of time. If you find this kind of slow journey relaxing or interesting, or simply a pleasant way to unwind, I'd be grateful if you gave the video a like, and maybe subscribe to the channel. It helps this quiet little space reach more people who might enjoy drifting off while learning something new about the world. Now, with that said, let's ease into the story. To understand how a lake could flood vast regions of the planet, we need to step back, not just centuries, but thousands of years, to a time when the Earth looked very different from today. At the end of the last ice age, enormous glaciers still covered much of the northern hemisphere. These weren't small mountain glaciers or scattered ice fields. They were continental ice sheets, vast layers of frozen water stretching for thousands of kilometers, thick enough in places to bury entire mountain ranges beneath them. If you had been able to stand on top of one, the view in every direction would have been a white horizon, gently rolling like a frozen ocean, silent except for the faint groaning and shifting of ice moving almost too slowly to see. The world was warming though, not quickly, not dramatically in any one year, but steadily enough that the edges of those ice sheets began to retreat. Summer sunlight lingered longer, winters softened slightly. Meltwater began to collect wherever the ice pulled back, filling lowlands and valleys, pooling in depressions left behind by the grinding movement of glaciers. Water, as it turns out, is patient. It fills whatever space is available, rising little by little, spreading outward, searching for the lowest paths. In the central part of North America, something remarkable began to take shape. As the Great Laurentide ice sheet melted along its southern edge, meltwater gathered in enormous quantities. Rivers carried water away at first, but the ice itself blocked many of the natural drainage routes. The land, still weighed down by the massive ice sheet to the north, sloped in unusual ways, creating basins where water could collect. Over time, those basins filled, and kept filling. What formed there was not just a lake in the ordinary sense, but a body of water so vast that modern comparisons struggle to capture it. This was Lake Agassiz, a lake that at times covered hundreds of thousands of square kilometers, larger than many countries that exist today. Picture that for a moment. Try to imagine looking across water that stretched farther than any shoreline you've ever seen. Not an ocean with waves and tides, but an inland sea, calm in many places, shallow in others, fed constantly by meltwater pouring down from the ice. Shorelines shifted as the ice retreated, and the lake grew in stages, sometimes draining partially, then filling again, reshaping itself over centuries. To anyone living nearby, If there had been people close enough to observe its full extent, it might have seemed permanent, as if it had always been there and always would be. But nature rarely holds things in perfect balance forever. The ice that contained Lake Agassiz was not solid, in the way a stone dam is solid. It was constantly moving, slowly flowing under its own immense weight. Glaciers are not frozen statues. They behave more like extremely thick rivers, creeping forward or retreating depending on temperature, snowfall, and the warmth of the seasons. As the climate continued to warm, the balance between ice and water became more delicate. Meltwater didn't just collect in the lake. It also seeped into cracks, widened channels beneath the ice, and pressed against frozen barriers that were never meant to hold back such volumes. Pressure built, year after year, silently and invisibly. It's easy to think of natural disasters as sudden, explosive events, but many of them are actually the result of very slow changes reaching a tipping point. A hillside weakens grain by grain before a landslide. Stress accumulates along a fault line for centuries before an earthquake, and in this case, water gathered quietly, persistently behind walls of ice. At some point, those walls began to fail. Scientists today study the evidence left behind because no one was there with instruments to record the moment. Instead, the clues are written in the land itself. Vast channels carved into bedrock, layers of sediment deposited far from their source, patterns in the seafloor that reveal sudden pulses of fresh water entering the oceans. All of these traces tell the same story. The lake did not simply drain gently. It burst, releasing enormous volumes of water in a relatively short period of time, reshaping landscapes and possibly even altering the climate of the entire planet. We'll take our time exploring how that happened and what followed. But before we move further into the mechanics of the flood itself, it helps to linger a little longer in the world that existed just before it. The Late Ice Age was a place of contrasts. In some regions, glaciers still dominated the land, reflecting sunlight and keeping temperatures cool. In others, newly exposed ground supported grasses, shrubs, and wandering herds of animals adapted to cold climates. Massive mammals still walk the plains in some areas, creatures that seem almost mythical now, but were very real at the time. Rivers ran differently, coastlines were not where they are today, and the land itself was still adjusting to the immense weight that had pressed down on it for thousands of years. When an ice sheet melts, the ground beneath it slowly rebounds, rising over centuries like a cushion regaining its shape. This process, called isostatic rebound, was already underway in some places, subtly changing drainage patterns and the paths water would follow. All of these factors mattered, because the fate of Lake Agassiz depended not on a single event, but on a combination of warming temperatures, shifting land, and the slow weakening of ice barriers that had once seemed immovable. It's interesting, in a quiet way, to think about how many of the largest changes in Earth's history begin with processes that are almost invisible day to day. A millimetre of melting here, a slight change in the flow of a river there, a summer a little warmer than the last. None of it feels dramatic in the moment, yet over decades and centuries, those small changes accumulate until the world looks completely different. Perhaps that's one reason stories like this feel calming to listen to. They unfold on timescales so vast that they remind us how patient the planet is, how slowly most transformations really happen, and how brief a single human lifetime is by comparison. If you imagine standing near the shores of that immense lake, long before the flood, you might hear only wind moving across water, the distant cracking of ice far to the north, and the steady flow of meltwater streams feeding the basin. Nothing about the scene would hint at the sudden violence that was possible, and yet, deep beneath the surface, pressure was building. Water is heavy. A cubic metre weighs a metric ton. Multiply that by the unimaginable volume contained in a lake the size of Lake Agassiz, and the force pressing against its boundaries becomes easier to appreciate. Ice, strong as it may seem, has limits. It fractures. It melts. It shifts under stress. At some point, a channel likely opened, perhaps beneath the ice, perhaps along its edge. Once water begins to flow through such a channel, it erodes and enlarges it rapidly. More water escapes, increasing the flow, widening the passage even further in a self-reinforcing cycle. What begins as a trickle can become a torrent. Long before the lake reached its greatest size, before the flood and the sudden release of water, the planet itself was in the middle of a slow and steady transition. To picture what was happening, it helps to imagine Earth not as the familiar map we know today, but as a colder world, still shaped in many places by the lingering grip of ice. Roughly 20,000 years ago, enormous glaciers covered vast regions of the northern hemisphere. These ice sheets were not just scattered patches of frozen ground. They were continental in scale, thick enough in places to reach several kilometers from base to surface, and wide enough to stretch across entire regions that today hold forests, cities, and farmland. The Laurentide ice sheet alone spread over much of what is now Canada, and extended deep into parts of the northern United States. If someone could have looked down from far above, the northern half of the continent would have appeared pale and bright, reflecting sunlight back into space. Ice has that effect. It acts like a mirror, sending a large portion of the sun's energy away rather than absorbing it. This reflection helped keep the planet cooler, reinforcing the icy conditions that allowed those glaciers to exist in the first place. But climates are rarely fixed. Even during an ice age, temperatures rise and fall over thousands of years. The last glacial maximum, the coldest point of the last ice age, had already passed. Gradually, almost imperceptibly at first, the balance began to shift. Summers grew slightly warmer. Snow that once lingered year-round began to melt at the edges of the ice sheets. The change was subtle enough that no single generation would have noticed it clearly, yet over centuries the effect was unmistakable. Glaciers began to retreat. When ice retreats, it does not simply vanish. It melts, and all that melt water has to go somewhere. Rivers carried some of it away, carving channels and transporting sediment. In other places, water pooled in low-lying basins left behind by the grinding movement of glaciers. These basins were common because glaciers are powerful sculptors of land. As they move, they scrape away soil and rock, deepening valleys and creating depressions that can later fill with water. Many of the lakes across Canada and the northern United States today owe their existence to that process. But in the late Ice Age, some of those lakes were far larger than anything we see now. At the same time, the land itself was behaving in a way that might seem surprising. During the height of the Ice Age, the sheer weight of the ice sheets pressed down on the Earth's crust. Imagine placing a heavy book on a soft cushion. The cushion compresses beneath it. In a similar way, the crust beneath the glaciers sank slightly under the immense load of ice. As the ice melted, that pressure eased and the land began to rise again. This process is called isostatic rebound, and it happens very slowly, often continuing for thousands of years after the ice disappears. The important detail here is that the land did not rebound evenly or instantly. Some areas rose faster than others, some remained depressed longer. This uneven movement altered the slopes of river valleys and the paths water would naturally take. In some cases, meltwater found its usual drainage routes blocked or redirected, causing it to accumulate instead of flowing freely to the sea. That was one of the key ingredients in the formation of enormous proglacial lakes like Lake Agassiz. Water collected not just because there was a lot of melting ice, but because the geography of the land and the presence of remaining glaciers prevented easy drainage. The climate of this period was also changing in ways that affected ecosystems across the planet. As temperatures warmed, vegetation began to spread into areas that had previously been too cold to support it. Grasses and hardy shrubs colonized newly exposed ground. Over time, small forests began to appear in regions that had once been tundra. Animals followed the shifting landscapes. Herds of grazing mammals moved into newly opened territories, feeding on the fresh plant growth that followed the retreating ice. Predators followed the herds. Life, in a quiet and steady way, expanded into spaces that had been locked in ice for thousands of years. It is worth pausing for a moment to consider how different that world would have looked and felt compared to today. Coastlines were not where they are now, because so much water was still locked in ice sheets that global sea levels were significantly lower. Land bridges connected regions that are now separated by water. The Bering Land Bridge, for example, linked Asia and North America, allowing animals and humans to migrate between continents. Rivers flowed along different courses. Winds carried dust from glacial outwash plains. In some places, the air itself may have felt different, colder and drier, especially near the edges of the great ice sheets. And always there was water. Meltwater streams ran along the margins of glaciers, sometimes disappearing into tunnels beneath the ice, sometimes spilling into growing lakes that expanded year by year. Lake Agassiz was one of the largest of these lakes, but it was not alone. Other proglacial lakes formed in different parts of the world wherever retreating ice blocked natural drainage. Most of them drained gradually as outlets opened and rivers carried water away. But Lake Agassiz was unusual, both in its size and in the way it was contained. To understand why, it helps to think about how glaciers behave at their edges. The margin of a large ice sheet is not a neat, solid wall. It is an irregular boundary of ice cliffs, meltwater channels and debris. Ice carves and breaks, melts and refreezes, shifts and creeps. In places, it forms natural dams, holding back lakes that rest against its edge. These ice dams can be surprisingly strong for a time. The weight of the glacier presses downward, sealing gaps and resisting the pressure of water behind it. But they are also vulnerable. Warmer temperatures increase melting. Water can seep into cracks, widening them. The ice itself continues to move, slowly deforming under its own weight. All of these processes were happening quietly during the centuries when Lake Agassiz existed. Another factor worth considering is the sheer scale of time involved. When we talk about the end of the Ice Age, it can sound like a brief event, but in reality it unfolded over thousands of years. Entire landscapes transformed gradually. Lakes expanded and contracted. Rivers changed course. Forests advanced northward at a pace so slow that it would have been almost impossible to notice from one year to the next. This slow pace has a way of calming the imagination. It reminds us that not all change is sudden, and that the planet often reshapes itself in ways that are steady and patient. Yet even in a world of gradual change, there are moments when conditions align and something dramatic occurs. One of the reasons scientists study this period so carefully is that it provides insight into how sensitive the climate system can be. Small shifts in temperature can lead to large changes in ice cover. Changes in ice cover can alter ocean circulation and atmospheric patterns, and large releases of fresh water, like the one that would eventually come from Lake Agassiz, can disrupt the delicate balance of currents that distribute heat around the planet. We will come back to that connection later because it plays an important role in understanding why this ancient flood matters even today. For now, it is enough to picture the setting. A continent emerging from ice, a climate in transition, enormous glaciers retreating slowly northward, and meltwater gathering in vast, shallow basins. If you imagine standing on a rise overlooking part of that landscape, you might see braided rivers carrying sediment-laden water, their channels shifting as sand and gravel accumulated along their banks. You might hear the distant rumble of ice breaking somewhere far away, a deep, echoing sound that carried across the open land. The air might feel cool, even in summer, especially near the glaciers, where cold winds flowed outward from the ice. And beyond all of that, stretching to the horizon, there would be water, a lake so large that weather systems could form above it, winds stirring waves along shorelines that extended farther than the eye could follow. It is a peaceful image in many ways, and for long stretches of time, the lake truly was peaceful. Shorelines stabilized, sediment settled, ecosystems developed along its edges, birds nested in wetlands. Plants took root in soils left behind as waters receded temporarily in some areas. Nothing in that quiet scene would have suggested how unstable the balance really was. because behind the calm surface of the lake stood the ice, and behind the ice lay the forces that had shaped the entire ice age itself. Temperature, gravity, and the steady pull of water were all working slowly and persistently to change the system. The ice sheet was thinning, its margins were retreating. Channels of meltwater were forming and reforming beneath it. At some point, those channels would connect in ways that allowed water to escape more rapidly than before. We will look closely at how scientists think that process unfolded because it involves an interesting combination of geology, hydrology, and a bit of careful detective work, reading clues left in the land thousands of years ago. But before we move into the mechanics of the lake itself, there is one more detail about the end of the Ice Age that helps set the stage. The climate was not warming smoothly. There were fluctuations, periods when temperatures rose more quickly, followed by intervals of relative cooling. These variations affected how fast glaciers melted and how much water flowed into lakes like Agassiz. In other words, the system was not steady. It was dynamic, constantly adjusting, sometimes in ways that amplified change rather than dampening it. That kind of instability is often what leads to sudden events in natural systems. Pressure builds gradually, but release can come quickly. Long before the floodwaters began to move, before vast currents carved channels across the land, there was simply a basin, a slow gathering of water, and a set of conditions that allowed something extraordinary to form. To understand Lake Agassiz, it helps to begin with the landscape itself, because the lake was not created by a single dramatic event. It was born gradually, the way many of Earth's largest features come into existence, through the quiet accumulation of small processes repeating over long stretches of time. As the Great Laurentide ice sheet retreated northward at the end of the last ice age, it left behind a surface that had been deeply altered by thousands of years of glacial movement. Ice does not merely rest on the land, it reshapes it. Beneath a glacier, rock is ground into fine sediment, hills are flattened, and depressions are carved into the surface. When the ice melts away, those depressions often become the basins that hold lakes. In central North America, the terrain left behind by the retreating ice sheet was particularly well suited for water to collect. The ground there had been pressed downward under the immense weight of ice, forming a broad, shallow basin. At the same time, the northern edge of this basin was still blocked by the remaining glacier, which acted like a natural dam. Meltwater from the ice had nowhere to go but into the lowlands to the south. At first, the water gathered in small pools and channels, feeding rivers that flowed along the margins of the glacier. But as melting continued, those pools merged and expanded. Year after year, the water level rose, spreading outward across the flat terrain. Eventually, the separate bodies of water joined into a single, enormous lake. Lake Agassiz did not appear all at once. It grew in stages, expanding and contracting as the ice margin shifted and new outlets opened or closed. Sometimes the lake drained partially through a temporary channel, lowering its level. Then the glacier would advance slightly, or block the outlet again, and the water would begin to rise once more. Over centuries, these cycles repeated, and the lake reached different sizes at different times. At its largest, Lake Agassiz covered an area greater than all of today's Great Lakes combined. Its surface extended across what are now parts of Manitoba, Ontario, Saskatchewan, North Dakota, and Minnesota. To someone standing on its shore, it would have looked less like a lake and more like an inland sea, its far edge lost beyond the horizon. It is difficult to picture something on that scale without a point of comparison. Imagine the distance from one major city to another, perhaps hundreds of kilometers apart, and then imagine that entire space filled with water, stretching uninterrupted in every direction. That was the reality of Lake Agassiz at its peak. The depth of the lake varied. In some places, especially near the southern and western edges, it was relatively shallow, spreading across flat plains. In other areas, where glacial erosion had carved deeper basins, the water reached considerable depths. Winds blowing across such a vast surface could generate waves large enough to reshape shorelines. piling up ridges of sand and gravel that can still be seen today. Those ancient shorelines remain one of the clearest pieces of evidence for the lake's existence. Long curving ridges known as beach ridges mark the positions of former shorelines, tracing the changing levels of the lake over time. If you travel across parts of the Canadian prairies or the northern United States today, you can sometimes see these ridges running across the landscape, subtle but unmistakable signs that water once stood there. Another remarkable feature of Lake Agassiz was the amount of sediment carried into it by meltwater streams. Glaciers grind rock into fine particles, creating what is known as glacial flour, a pale, powdery sediment that turns meltwater cloudy. Rivers flowing into the lake carried enormous quantities of this material, which settled slowly to the bottom. Over thousands of years, these sediments formed thick layers of clay and silt across the lake bed. Today, those former lake beds are among the most fertile agricultural regions in North America, their soils enriched by the fine sediments deposited in the quiet waters of the ancient lake. It is interesting to think that farmland, crops and towns now occupy areas that were once submerged beneath hundreds of meters of water, their flatness a legacy of the lake that once lay there. The water of Lake Agassiz itself was cold, fed by melting ice, and often filled with suspended sediment. Near the glacier's edge, the water might have been milky with fine particles, while farther from shore it cleared somewhat as the sediment settled. Floating icebergs would have been a common sight in parts of the lake, especially near the northern margins. As sections of the glacier broke away, they drifted slowly across the water, melting gradually in the warmer air. These icebergs carried rocks and debris frozen into them, and when they melted, the debris dropped to the lake bed, leaving behind isolated stones known today as drop stones, another clue to the lake's glacial origins. The climate around the lake was still cool compared to modern conditions, but it was warming. Summers were becoming longer and milder, and vegetation was spreading across newly exposed land. Grasses and small shrubs took root along the shores, followed gradually by stands of trees in regions where the climate allowed. Wildlife would have been abundant in some areas, drawn by the availability of water and fresh vegetation. Migratory birds likely used the lake as a stopover, just as they use large lakes today. Herds of grazing animals may have moved along the shorelines, feeding in the wetlands that formed where rivers entered the lake. It is possible that early humans lived in regions near the southern edges of Lake Agassiz, although the evidence is limited and often fragmentary. The people of that time were mobile, following animal herds and adapting to changing landscapes. To them, the lake would have been a vast and perhaps intimidating presence, its far shores invisible, its northern horizon dominated by the gleaming wall of ice. One of the most fascinating aspects of Lake Agassiz is how dynamic it was. Unlike many modern lakes, whose shorelines remain relatively stable over human timescales, this lake was constantly changing. As the glacier retreated, new areas opened for water to fill. As outlets formed or were blocked, the lake level rose or fell, sometimes by many meters. Scientists have identified multiple stages of the lake, each corresponding to a different configuration of ice margins and drainage routes. These stages are named after locations where evidence of ancient shorelines has been found, and they help reconstruct the history of the lake's growth and transformation. At times, the lake drained southward through river systems that eventually connected to the Mississippi River and the Gulf of Mexico. At other times, drainage shifted eastward or northward as the ice retreated and new pathways opened. Each change altered the size and shape of the lake, sometimes dramatically. This shifting pattern of drainage is important because it meant that Lake Agassiz was not just a static body of water waiting to burst. It was part of a complex system, interacting with glaciers, rivers, and the changing topography of a continent emerging from ice. The lake's northern boundary remained the most critical factor in its existence. As long as the ice sheet blocked the lower outlets to the north, water accumulated in the basin. But the glacier itself was thinning and retreating, and beneath it, meltwater was carving channels and weakening the ice from below. It is easy to think of ice as rigid and immovable, but in reality, it is surprisingly responsive to pressure and temperature. Water flowing beneath a glacier can erode the bedrock and lubricate the ice above, increasing its movement. Cracks can propagate through the ice, and entire sections can collapse or float when enough water accumulates beneath them. Over time, these processes created conditions where large volumes of water could escape suddenly if a stable outlet opened or an ice dam failed. But before that happened, Lake Agassiz reached its greatest extent, a true giant among lakes, holding an astonishing volume of fresh water. To put that volume into perspective, estimates suggest that the lake contained more water than all the modern Great Lakes combined. That is an immense amount of water, enough to influence sea levels and ocean circulation if released rapidly, and that is exactly why scientists study Lake Agassiz so carefully today. The lake was not just a geographical curiosity, it was a reservoir of fresh water capable of affecting the entire climate system if discharged quickly into the oceans. Standing on the edge of a body of water is usually a simple experience. You see waves, perhaps a distant shoreline, maybe ships or birds moving across the surface. Even the largest lakes most people know still have limits that the eye can sense. The far shore might be faint, but it is there, a thin line that reminds you the water ends somewhere. Lake Agassiz was different in a way that is difficult to grasp at first, because in many places there was no visible opposite shore at all. The horizon was water and sky, and nothing in between. To understand just how large this lake was, it helps to step away from maps and think in distances that feel familiar. Imagine travelling for hours across flat land, fields and forests passing by, towns appearing and disappearing, and all of that terrain being underwater instead. At its greatest extent, Lake Agassiz covered more than 400,000 square kilometres. That is larger than many modern countries. If placed on a present-day map of Europe, it would stretch across entire regions, submerging landscapes that today hold millions of people. Numbers alone can feel abstract, so it helps to visualize the geography in another way. The lake spread across what is now Manitoba, large parts of Ontario and Saskatchewan, and deep into the northern United States. The Red River Valley, the Lake of the Woods region, and vast prairie lowlands all lay beneath its waters at different times. What is now farmland, highways, and small towns was once the bottom of a quiet inland sea. The shoreline itself was never fixed. Because the land was still slowly rising in some areas, and the ice sheet continued retreating in others, the lake's boundaries shifted. At times it expanded northward as new basins opened. At other times it spilled through temporary outlets and shrank, only to fill again when those outlets closed. Over centuries the waterline moved back and forth, leaving behind ridges of sand and gravel that still mark its ancient beaches. If you travel today across parts of the Canadian prairies, you may notice long, gentle rises in the land that seem out of place, curving across otherwise flat terrain. These are not hills formed by tectonic forces or wind-blown dunes. They're old shorelines, built by waves thousands of years ago when the water stood much higher. Each ridge is a quiet record of where the lake once reached, like rings marking the changing level of a bathtub, only stretched across entire provinces. Depth varied widely across the lake. In many places it was shallow, spreading across flat plains in water perhaps tens of meters deep. In others, especially nearer the former ice margins or in deeper glacial basins, the water reached far greater depths. Wind moving across such a vast surface could generate powerful waves, and storms would have rolled across the lake much as they do over modern inland seas like Lake Superior. Because the lake was so large, weather patterns could develop over it independently of surrounding land. Warm air passing over the water could form clouds and storms, while colder air near the glacier's edge would create sharp contrasts in temperature. Someone living near its shores might have experienced sudden winds sweeping in from the open water, carrying the smell of wet sediment and the faint chill of melting ice. The scale of the lake also meant that its influence on the surrounding environment was enormous. Large bodies of water moderate temperature, absorbing heat during the day and releasing it slowly at night. Areas near the shoreline may have experienced milder conditions than regions farther inland, with fewer temperature extremes. This effect, familiar today around large lakes, would have shaped local ecosystems, influencing which plants could grow and which animals could thrive. Rivers flowing into Lake Agassiz were themselves impressive. Meltwater streams emerging from the glacier carried huge loads of sediment, turning the water cloudy with fine particles of ground rock. These rivers spread into wide deltas where they entered the lake, depositing layers of silt and clay that gradually built outward into the basin. Over time, these sediments settled across the lake bed, forming the fertile soils that now support agriculture in regions like the Red River Valley. The water itself was constantly renewed. Glacial melt poured into the lake each summer, and even in winter, subglacial streams continued to feed it from beneath the ice. This steady inflow meant that Lake Agassiz was not a stagnant body of water. Currents moved slowly within it, driven by wind and the temperature differences between incoming meltwater and the surrounding lake. Icebergs were a common feature in many parts of the lake, especially closer to the glacier. When large chunks of ice broke away from the ice sheet, they drifted out onto the lake, sometimes carrying rocks frozen into them. As the ice melted, those rocks fell to the bottom, leaving isolated stones in otherwise fine sediment. Today, geologists find these drop stones and use them as evidence of the lake's glacial environment. Life around the lake was shaped by its presence. Wetlands formed along the shores, providing habitat for birds and small animals. Vegetation colonized exposed areas as water levels shifted, and herds of grazing mammals may have moved along the edges where grasses grew in newly uncovered soil. For early human groups travelling through the region, the lake would have been both a barrier and a resource, offering water and food, but also limiting movement across the land. It is interesting to think about how such a vast feature might have influenced the people who lived nearby. A lake this large would have dominated the horizon, shaping travel routes and seasonal migrations. Crossing it would have been impossible without boats, and going around it could take days or weeks. To those who saw it, it may have seemed as permanent as the sky. Yet permanence is often an illusion in geology. Even features that appear stable over a lifetime can change dramatically over longer timescales. Lake Agassiz itself was evidence of that truth, formed by melting ice that had once seemed equally permanent. One of the most remarkable aspects of the lake's size was the sheer volume of water it contained. Estimates vary, but at its largest, Lake Agassiz may have held more fresh water than all of today's Great Lakes combined. That is an extraordinary amount of water, enough that its sudden release could alter sea levels and disrupt ocean currents far from the lake itself. Scientists study ancient shorelines, sediment layers, and drainage channels to reconstruct how large the lake was at different times. By mapping these features and dating the sediments, they can estimate water levels and track how the lake expanded and contracted over thousands of years. This work requires patience and careful observation, piecing together clues left behind in the landscape like fragments of a very old puzzle. Satellite imagery has made this work easier in recent decades. From space, the faint lines of former shorelines become more visible, tracing graceful arcs across plains and forests. These patterns reveal the outlines of the lake at various stages, showing just how far its waters once reached. Another clue comes from the composition of soils. The fine clays and silts deposited in the quiet waters of Lake Agassiz differ from the coarser sediments found in river valleys or glacial deposits. By studying these soils, geologists can map the extent of the ancient lake bed, confirming how widespread it was. All of this evidence tells the same story. Lake Agassiz was not merely large, it was enormous on a continental scale, a body of water that shaped landscapes, ecosystems, and eventually even climate. Despite its size, however, the lake was vulnerable. Its existence depended on a delicate balance between the inflow of meltwater and the barriers that prevented that water from draining away. The glacier to the north acted as a dam, but it was a dam made of ice, constantly melting, cracking and shifting. Water levels rose and fell over time, sometimes dramatically. When new outlets opened, the lake could drop by many meters, exposing wide stretches of former lake bed. When those outlets closed again, the water would rise, flooding the land once more. These fluctuations left a complex pattern of shorelines at different elevations, evidence of the lake's changing size. Each ridge and terrace marked a period when the water stood at a particular level, sometimes for centuries, sometimes for shorter intervals. What makes this story especially fascinating is that all of these changes were happening in a world already undergoing rapid transformation. The climate was warming, ice sheets were retreating, and ecosystems were shifting northward. Lake Agassiz was part of that larger process, a temporary feature created by the retreat of ice and destined to disappear as the landscape continued to evolve. For a long time, though, it remained, vast and quiet, its surface reflecting the sky, its northern boundary pressed against the shimmering wall of the glacier. Winds moved across it, waves broke along its shores, and meltwater continued to pour in from the north. And slowly, almost imperceptibly, the conditions that would eventually lead to its greatest transformation were taking shape, because the same forces that created the lake were also working to undermine the barriers that held it in place. Far to the north of the lake's broad waters, beyond the quiet shorelines and the drifting icebergs, there stood a barrier unlike anything we usually imagine when we hear the word dam. It was not built of stone or earth, and no human hand had shaped it. This barrier was part of the Laurentide ice sheet itself, a massive wall of ice that stretched for hundreds of kilometers, rising in places like a frozen cliff, and in others sloping gently upward into a white expanse that seemed to merge with the sky. That ice wall was the reason Lake Agassiz could exist at all. Without it, meltwater would simply have drained northward into the Arctic basin, spreading through river valleys and reaching the sea without ever forming such a vast inland body of water. The glacier, immense and cold, blocked those routes, turning the lowlands to the south into a basin that steadily filled. It is useful to pause and consider what a glacier of that scale really is. Ice sheets are not static blocks, and they are not brittle in the way frozen water in a household freezer is brittle. Under the immense pressures of their own weight, glaciers behave almost like very thick, slow-moving fluids. They flow outward from their centres, creeping across the land at speeds that are usually measured in meters per year, sometimes faster, sometimes slower, but always moving. Because of this movement, the margin of an ice sheet is never perfectly still. It advances during colder periods, retreats during warmer ones, and constantly reshapes itself through melting, cracking, and refreezing. Meltwater flows across its surface in summer, carving channels that can plunge downward into vertical shafts called moulins, carrying water deep into the glacier's interior. Beneath the ice, streams can form and flow along the bedrock, lubricating the base and allowing the glacier above to slide more easily. All of these processes were happening along the northern edge of Lake Agassiz. The ice dam was not a simple wall. It was a complex and changing structure, riddled with channels, crevasses, and zones of weakness that evolved over time. Despite this, ice dams can be remarkably effective at holding back water, at least for a while. The weight of the glacier presses downward, sealing gaps and resisting the pressure of the lake. Cold temperatures help maintain the integrity of the ice, and as long as melting does not outpace the glacier's ability to flow and replenish itself, the barrier can remain stable for centuries. Lake Agassiz existed in this kind of uneasy balance. Meltwater poured into it year after year, raising its level, while the ice margin to the north held firm, at least on the surface. To anyone observing from the shoreline, the lake might have seemed permanent, the glacier an unchanging presence at the horizon. But beneath that appearance of stability, forces were at work that would eventually lead to failure. Water exerts pressure, and the deeper it becomes, the greater that pressure is. At the base of the lake, the weight of the water pressed against the ice dam with tremendous force. Even a small crack or channel could become the starting point for erosion, as water forced its way through, melting and widening the passage. This process is known as subglacial drainage, and it plays a crucial role in the life cycle of glaciers. Water flowing beneath the ice can carve tunnels, sometimes large enough to carry entire rivers. These tunnels are not stable in the long term, because the ice around them can deform and close, but while they exist, they provide pathways for water to escape. In the case of Lake Agassiz, such pathways may have formed repeatedly, allowing partial drainage events that lowered the lake level before the outlets closed again. Geological evidence suggests that the lake went through multiple stages, expanding and contracting as drainage routes opened and shut. Still, the largest flood would require something more dramatic than the slow enlargement of a subglacial channel. It would require a breach large enough to release enormous volumes of water in a relatively short period of time. To understand how that could happen, it helps to think about the structure of an ice dam in more detail. Unlike a rock barrier, which is anchored firmly to the ground and resists deformation, ice is sensitive to temperature. Even a small increase in warmth can weaken it, especially near the surface where melting occurs. Meltwater can seep into crevasses, refreeze at night, and expand, widening the cracks. Over time, networks of fractures can develop, creating zones where the ice is significantly weaker than the surrounding areas. At the same time, the glacier itself continues to move. This movement can place stress on certain regions, stretching the ice and making it more prone to breaking. Large chunks can carve off, especially where the glacier meets open water. Anyone who has watched modern glaciers at the edges of polar regions has seen this process. Enormous slabs of ice breaking away and crashing into the sea. Along the margin of Lake Agassiz, similar events would have occurred, though perhaps less dramatically visible from a distance. Pieces of the ice front may have collapsed into the lake, sending waves across the water and exposing fresh surfaces to melting. Another factor that weakened the ice dam was the warming climate itself. As temperatures rose at the end of the Ice Age, melting accelerated not only on the surface of the glacier, but also at its base. Warmer air, warmer water, and increased meltwater flow all contributed to thinning the ice. Thinner ice means less pressure holding the dam in place, and greater vulnerability to fracture. It also means that the glacier's margin retreats, sometimes unevenly, exposing new areas where water can find routes around or beneath the barrier. In some cases, lakes held back by ice dams drain gradually, their waters finding a stable outlet that allows them to empty without catastrophic flooding. In other cases, the drainage is sudden and violent, releasing water in a torrent that reshapes the landscape. What determines which outcome occurs depends on many factors: the size of the lake, the height and strength of the dam, the rate of melting, and the presence of pre-existing channels or weaknesses. Lake Agassiz was so large that the pressure against its ice dam was immense. Once a significant breach began, the force of the escaping water would have eroded and enlarged the opening rapidly, turning a modest flow into a massive outburst. It is also worth remembering that the glacier was not the only barrier involved. In some regions, the surrounding land formed natural boundaries that guided the lake's waters, directing them towards certain outlets while blocking others. As the land slowly rebounded from the weight of the ice, these pathways changed, altering the routes available for drainage. Scientists today study ancient spillways, enormous channels carved into bedrock and sediment, to determine where the water went when it finally escaped. Some of these channels are far larger than any modern river, clear evidence that they were formed by flows of extraordinary magnitude. Standing in one of those dry channels today, with grass and trees growing along its floor, it can be difficult to imagine the volume of water that once rushed through. Yet the scale of the landforms leaves little doubt. Only a flood of immense size could have carved valleys tens of kilometers wide and scoured the ground down to bare rock. The ice wall that once held back Lake Agassiz did not fail in a single instant like a glass shattering. More likely, it weakened over time, its structure compromised by melting, fracturing, and the relentless pressure of water. At some point, a threshold was crossed, and the barrier could no longer contain the lake. Before we follow that moment of release, there is another detail about ice dams that helps explain why their collapse can be so sudden. When water begins to flow through a channel in ice, the flow generates heat through friction and turbulence. That heat melts the surrounding ice, enlarging the channel and allowing even more water to pass through. This feedback process can accelerate rapidly, turning a small leak into a major outflow in a matter of days or even hours. In addition, as the water level in the lake begins to drop, the pressure at the base of the glacier changes, sometimes destabilizing the ice further and causing sections to collapse. The result can be a cascading failure, with the dam breaking apart in stages as the flood intensifies. It is a reminder that natural systems often behave in non-linear ways. For long periods, changes may be slow and gradual, but once certain thresholds are crossed, the pace can increase dramatically. All of this was part of the story of Lake Agassiz, though the exact sequence of events is still a subject of research and debate. The evidence preserved in sediments, landforms, and ocean records provides strong clues, but the details of each drainage event remain partly hidden in the distant past. What is clear is that the ice wall, vast and imposing as it was, could not hold forever. The climate continued to warm, the glacier continued to thin, and the lake continued to press against its boundaries. Change rarely announces itself loudly at first. More often, it begins with small shifts that are easy to overlook, especially in landscapes as vast as those shaped by glaciers. The frozen barrier that held Lake Agassiz in place did not suddenly fracture in a single dramatic instant. Instead, it began to weaken gradually, in ways that would have been almost invisible to anyone standing nearby, even over the course of many years. To understand how this weakening began, it helps to picture the glacier not as a rigid wall, but as a living system of ice in motion. A continental ice sheet is constantly adjusting to temperature, snowfall, and the flow of ice from its interior toward its edges. At the margins, where the glacier meets open land or water, the balance is especially delicate. Ice melts more quickly there, and the flow from upstream may not always keep pace with the loss. As the climate warmed near the end of the Ice Age, summer melting increased. Each year, more water flowed across the glacier's surface, forming streams that cut shallow channels into the ice. Some of that water pooled in depressions, forming temporary lakes on the glacier itself. When these lakes found cracks or vertical shafts, the water drained downward, sometimes reaching the base of the ice thousands of meters below. Water at the base of a glacier plays a powerful role. It reduces friction between the ice and the ground, allowing the glacier to slide more easily. It can also carve channels beneath the ice, gradually enlarging them as the flow continues. Over time, these hidden waterways form complex drainage systems, constantly changing as channels open, close, and shift. Along the northern edge of Lake Agassiz, such processes were quietly at work. Meltwater seeped into fractures in the ice dam, widening them little by little. Some channels carried water away harmlessly, lowering the lake slightly or redirecting flow into other basins. Others may have remained small, freezing shut during colder seasons, only to reopen when temperatures rose again. These cycles of melting and refreezing created zones of weakness in the ice. Cracks formed, sometimes extending deep into the glacier. The surface of the ice, once relatively smooth, became broken by crevasses and meltwater channels, signs of stress within the structure. At the same time, the glacier itself was thinning. Warmer temperatures meant that more ice melted each summer than was replaced by snowfall in winter. Over decades and centuries, this imbalance reduced the thickness of the ice sheet, especially near its margins. Thinner ice is less stable. It exerts less downward pressure, making it easier for water to lift or float sections of it from below. In some areas, the glacier's base may have begun to separate slightly from the ground, creating cavities where water could accumulate. Once water fills such spaces, it can flow more freely, eroding sediment and enlarging pathways that eventually connect the lake. Another subtle but important process was taking place beneath the land itself. The crust, still rebounding slowly after being compressed by the weight of ice, was changing the slopes of valleys and basins. These changes were gradual, measured in millimeters per year, but over centuries they altered the routes that water naturally followed. In some places, land that had once sloped gently northward began to tilt in ways that encouraged drainage in new directions. Low points shifted, and channels that had been blocked or ineffective began to offer potential pathways for water to escape. The combination of thinning ice and changing landforms created conditions that made the ice dam increasingly vulnerable. It is also worth considering the role of seasonal variation. During summer, melting was at its peak, and meltwater streams were at their strongest. The lake level rose, increasing the pressure against the ice barrier. In winter, freezing temperatures slowed surface melting, but water stored beneath the ice could continue to flow, insulated from the cold above. These seasonal cycles meant that stress on the ice dam was not constant. It increased and decreased throughout the year, much like pressure building and releasing in a slow rhythm. Over long periods, such repeated stresses can weaken materials, even those as massive as a glacier. Modern observations of glaciers in places like Greenland and Antarctica provide useful clues about how such weakening occurs. Scientists have watched large ice shelves develop networks of fractures that expand over time, sometimes leading to sudden breakups. In many cases, the final collapse appears abrupt, but the weakening process has been underway for years or even decades. The same principle likely applied to the ice barrier holding Lake Agassiz. Long before the flood, the glacier was already changing, its structure becoming more fragile as melting accelerated. Another factor that may have contributed to instability was the presence of floating ice near the margin. When water is deep enough, the edge of a glacier can begin to float, forming what is known as an ice shelf. Floating ice is more prone to cracking and breaking, especially when waves and currents act upon it. If parts of the glacier along the lake's edge began to float, even partially, the stability of the entire barrier would have been reduced. Cracks could propagate more easily, and sections of ice could detach, exposing fresh surfaces to melting and further weakening the structure. Meanwhile, within the lake itself, water levels were not perfectly stable. As inflow from melting ice varied with climate and season, the surface of the lake rose and fell. Each rise increased the pressure on the dam. Each fall relieved it slightly, but also changed the distribution of stress within the ice. These fluctuations may have caused small drainage events, releasing water through temporary channels that later closed. Geological evidence suggests that Lake Agassiz experienced several such partial outflows before the largest floods occurred. Each event may have altered the ice barrier in subtle ways, widening existing weaknesses or creating new ones. From a distance, the glacier might still have appeared solid and unchanging, its white expanse stretching across the northern horizon. But within it, cracks were forming, channels were widening, and the balance between ice and water was shifting. It is interesting to reflect on how such immense changes can begin quietly. A crack in ice a few centimeters wide might seem insignificant compared to a lake hundreds of kilometers across. Yet water has a way of finding the smallest openings, and once it begins to flow, it can transform a narrow passage into a broad channel with surprising speed. One way to visualize this process is to think of a small stream cutting into soil after a heavy rain. At first, the water follows a tiny depression, barely noticeable. As more water flows, the depression deepens, the banks collapse, and the stream grows wider and deeper. What begins as a trickle becomes a channel capable of carrying much larger flows. Under a glacier, the same principle applies, though the materials and forces involved are very different. Water melts ice as it flows, enlarging channels and increasing discharge. The more water that escapes, the faster the process can accelerate. There were also changes happening in the climate beyond the immediate region. Atmospheric patterns were shifting as the planet emerged from the Ice Age. Temperatures did not rise smoothly. There were intervals of faster warming and periods of relative stability. These fluctuations affected the rate at which glaciers melted and the amount of water entering lakes like Agassiz. At times of increased melting, the lake would have filled more rapidly, raising water levels and intensifying pressure on the dam. During cooler intervals, melting slowed, but the damage done to the ice during warmer periods remained. Over centuries, this pattern of warming, melting, cracking and refreezing gradually eroded the strength of the frozen barrier. If someone had been able to observe the glacier closely over many years, they might have noticed subtle changes. Crevasses widening slightly each summer, meltwater streams appearing earlier in the season, sections of ice calving more frequently into the lake. None of these signs alone would have foretold the scale of what was coming, but together they marked a system under increasing strain. The lake itself continued to grow and shift, its vast surface reflecting the sky, its shores expanding and contracting with changes in water level. Beneath the calm surface, the weight of the water pressed steadily against the ice, a constant force that never diminished. It is easy to imagine such pressure in mechanical terms, but there is also a quiet inevitability to it. Water seeks lower ground. Given enough time, it finds a path. The only question is when and how that path opens. By the time the largest floods approached, the ice dam had likely become a patchwork of stronger and weaker zones, some still thick and stable, others thin and fractured. Channels beneath the ice may already have been carrying significant flows, gradually enlarging and connecting in ways that brought them closer to the point of catastrophic release. Scientists studying ancient flood channels have found evidence of sudden, massive discharges that could only have occurred when large volumes of water were released in a relatively short time. These channels, carved into bedrock and sediment, provide a record of what happens when a glacial lake drains rapidly. But before that moment arrived, there must have been a period when the system was poised on the edge, neither fully stable nor yet in collapse. The cracks were there, the channels existed, the pressure was building. Somewhere along the immense length of the ice margin, conditions were approaching a threshold. Perhaps a subglacial channel widened beyond a critical point. Perhaps a section of ice collapsed, exposing a new outlet. Perhaps a combination of melting, thinning and rising water levels aligned in a way that allowed water to begin escaping faster than before. At some point after centuries of slow change, the balance could no longer hold. The ice barrier that had contained Lake Agassiz for so long had been thinning, cracking and shifting year by year, and the lake behind it had continued to rise and press outward with steady force. There was no single day marked on a calendar, no observer to record the exact hour, but geological evidence suggests that eventually a breach formed large enough that the flow of water began to accelerate beyond anything the glacier could resist. To picture that moment, it helps to think not of an explosion, but of a transition. For a long time, water may have been escaping in smaller amounts through subglacial channels, flowing beneath the ice in hidden tunnels. These flows would have been powerful in their own right, but still limited, constrained by the size of the passages carrying them. Then, at some critical point, one of those channels enlarged beyond the ability of the surrounding ice to close it again. Once that happened, the process began to reinforce itself. Water moving through a confined space generates friction and turbulence, both of which produce heat. In the case of a channel cut through ice, that heat melts the surrounding walls, widening the passage. A wider passage allows more water to flow, which increases the melting, which widens the passage further. It is a feedback loop, and once it begins in earnest, it can transform a narrow tunnel into a broad outflow in a surprisingly short time. The pressure of the lake behind the dam played a crucial role. The deeper the water, the greater the force pushing toward any opening. When the breach began to enlarge, the pressure forced water through with increasing speed, eroding ice, sediment and rock along the way. The outflow would not have been a gentle river, it would have been a torrent, dense with suspended sediment, cold and powerful, carrying chunks of ice and debris as it surged forward. At first, the lake level may have dropped only slightly, almost imperceptibly across such a vast surface, but as the channel widened and discharge increased, the rate of drainage would have accelerated. Water that had taken centuries to accumulate began to leave the basin far more quickly. Imagine standing near the outlet, if such a thing were possible, and hearing the sound of water rushing beneath or around the ice. It would not have been the steady murmur of a stream, but a deep, continuous roar, echoing through channels and cavities, accompanied by the cracking and shifting of ice under immense stress. Sections of the glacier near the breach may have begun to collapse as the supporting water pressure changed. Ice that had been partly buoyed by the lake could have settled or fractured, sending large blocks tumbling into the outflow. Each collapse would have enlarged the opening further, allowing even more water to escape. It is important to remember that the ice dam was not uniform. Some parts were thicker, stronger and colder, others were thinner, riddled with fractures, or resting on uneven ground. The breach likely exploited one of the weaker regions where melting and stress had already reduced the strength of the ice. As the opening expanded, the flow of water would have become unstoppable. The lake, immense though it was, could not resist gravity. Water always moves downhill when given the chance, and the pathways leading away from Lake Agassiz descended toward lower elevations that ultimately connected to the oceans. The speed of the flood is difficult to estimate precisely, but studies of similar glacial outburst floods suggest that discharge rates can reach millions of cubic meters per second. To put that into perspective, some of the largest rivers on Earth today carry tens of thousands of cubic meters per second. A megaflood can exceed that by orders of magnitude, releasing volumes of water that reshape landscapes in a matter of days or weeks. Channels carved by such floods provide some of the best clues about what happened. In regions downstream from the former lake, geologists have identified enormous spillways, valleys far larger than any river now flowing through them. The scale of these features indicates that the water moved with extraordinary force, capable of eroding bedrock and transporting massive amounts of sediment. As the lake drained, its surface would have lowered gradually but relentlessly. Shorelines that had existed for centuries were left high and dry. Wetlands became plains. Rivers that had once flowed gently into the lake found themselves cutting deeper channels as the water level fell. For anyone living near the southern edges of the basin, if there were people present at that time, the changes might have been noticeable over weeks or months rather than hours. The vastness of the lake meant that even a significant outflow would take time to lower the overall level. Yet near the breach itself, the transformation would have been dramatic, the landscape reshaped by currents too powerful to resist. Another consequence of the sudden drainage was the release of enormous amounts of sediment. Water leaving the lake carried fine clays and silts that had accumulated on the bottom, along with sand and gravel eroded from channels and shorelines. This sediment-laden water spread across downstream regions, depositing layers that can still be identified today. The flood did not necessarily occur in a single, uninterrupted event. Evidence suggests that Lake Agassiz experienced multiple major drainage episodes over time, each associated with different outlets as the ice sheet retreated and the land rebounded. Some of these floods may have been larger than others, depending on how much water was stored in the lake and which pathways were available for drainage. One of the largest releases is believed to have sent freshwater rushing toward the North Atlantic, potentially disrupting ocean circulation. That connection between the flood and global climate is something we will explore later, because it shows how events in one region can influence conditions across the planet. For now, it is enough to consider the mechanics of the breach itself, because it reveals how systems that appear stable can change rapidly once certain thresholds are crossed. The ice dam had been under pressure for centuries, cracks had formed, channels had developed, and melting had thinned the barrier. The lake behind it had grown enormous, storing a volume of water comparable to an inland sea. All the ingredients were present for a sudden release. What remained was the moment when those ingredients combined in just the right way. Perhaps a warm summer increased melting beyond the usual rate, sending larger volumes of water into subglacial channels. Perhaps a section of ice collapsed, opening a pathway that connected previously separate drainage routes. Perhaps land uplift altered the slope of an outlet, allowing water to begin flowing more freely in a particular direction. Any one of these factors could have contributed, and in reality it was likely a combination of several. Once the outflow began in earnest, the dynamics would have been governed by gravity and hydraulics. Water accelerates as it descends, especially when confined to channels. The force of the current erodes the channel bed and walls, enlarging the passage and allowing even more water to pass. This positive feedback continues until the lake level drops enough to reduce the pressure driving the flow. During the peak of the flood, the discharge may have rivaled or exceeded that of the largest floods known in Earth's geological record. The sound alone would have been extraordinary, a continuous thunder of water and ice, punctuated by the cracking of collapsing sections of glacier and the grinding of sediment carried along in the torrent. Downstream, the floodwaters spread across valleys and plains, carving new channels and deepening existing ones. The landscape changed rapidly, sometimes within days, leaving behind features that still bear the marks of those flows. Yet even as the flood reshaped the land, the process of drainage was gradually reducing the lake itself. As the water level fell, the pressure on the remaining ice decreased, and the rate of outflow eventually slowed. The Great Lake, which had taken centuries to form, diminished over a much shorter span of time. What remained was not a single empty basin, but a complex pattern of smaller lakes, rivers, and wetlands occupying the lowest areas of the former lake bed. The retreat of the glacier continued, opening new drainage routes and altering the configuration of water across the region. The failure of the ice dam was not the end of Lake Agassiz's story, but it was a turning point. From that moment onward, the lake's existence was temporary, its waters destined to find their way to the oceans as the climate warmed and the ice retreated further. It is remarkable to think about how such a vast body of water could disappear in stages, leaving behind fertile plains, winding rivers, and subtle ridges that mark former shorelines. The transformation was not instantaneous everywhere, but the breach itself marked the beginning of a new phase in the landscape's history. Events like this also remind us of the immense power stored in natural systems. Water, when gathered in sufficient volume and given a pathway downhill, can move mountains of sediment and reshape entire regions. The flood from Lake Agassiz was one of those rare moments when the quiet processes of accumulation gave way to sudden release. It helps to slow down for a moment and picture what it actually means for a body of water the size of an inland sea to begin moving, not rippling at the surface, not shifting with tides or wind, but draining, accelerating, and flowing across land in volumes so large that ordinary comparisons stop being useful. Rivers, as we usually know them, feel powerful, but they are narrow corridors of flow compared to what followed when Lake Agassiz began to release its water. When the outflow strengthened and the channels widened, the water did not travel as a single neat stream. It spread, divided, rejoined, and surged forward in enormous braided currents, filling valleys from side to side and sometimes spilling beyond them. The flood was not simply water moving through the landscape. In many places it was the landscape itself being reorganized under the force of moving water. To understand the scale, imagine a modern river valley, perhaps several kilometers wide, carrying a steady flow of water between its banks. Now imagine that valley filled completely, bank to bank and beyond, with water moving fast enough to carry boulders, trees, and sediment in suspension. Then imagine not one such valley, but multiple pathways, all carrying immense currents at the same time, fed by the continuous drainage of a lake that had taken centuries to fill. Estimates of peak discharge during the largest outburst from Lake Agassiz suggest flows that may have exceeded several million cubic meters of water every second. That number is difficult to picture, so it helps to compare it with something more familiar. The Amazon River, the largest river on Earth today, carries roughly 200,000 cubic meters per second on average. A megaflood can exceed that by an order of magnitude or more. Water moving at that scale behaves differently from the rivers we're used to seeing. The force of the current can strip soil down to bare rock, carve deep channels in a short time, and transport sediment across vast distances. Sand, gravel, and even large stones can be carried along, grinding against each other and against the bedrock, acting like a moving sheet of abrasive material. As the floodwaters surged forward, they followed the paths of least resistance, often exploiting existing river valleys but greatly enlarging them. In other places, the water overtopped divides and cut entirely new channels, reshaping drainage patterns that had existed for thousands of years. One of the remarkable features left behind by such floods is the presence of oversized valleys, channels far larger than the rivers that now occupy them. These valleys may be tens of kilometers wide, with steep sides and flat floors, clear evidence that the water which carved them was far greater in volume than anything seen today. The floodwaters did not move as a single wave travelling neatly from one place to another. Instead, the release of water from the lake created sustained flows that continued for days, weeks, or longer, depending on the size of the breach and the volume of water available. As long as the lake level remained high and the outlet remained open, the current continued. In some areas, the water spread out across low plains, forming temporary inland seas that advanced and retreated as the flood progressed. These shallow but fast-moving sheets of water could erode large areas of land, leaving behind scoured surfaces and deposits of sediment arranged in long, low ridges. In other places, the floodwaters plunged through narrow passages where valleys constricted the flow. There, the speed of the current increased dramatically, and erosion intensified. Bedrock was gouged and polished, and enormous potholes were drilled into the ground by swirling stones trapped in eddies. Modern examples of such features can be seen in regions affected by ancient megafloods, where the landscape still bears the marks of water moving with extraordinary power. These landforms are among the most convincing pieces of evidence for the scale of the floods that once occurred. It is also important to remember that the water leaving Lake Agassiz was not clear. It carried vast quantities of sediment eroded from the lake bed and from the channels through which it flowed. This sediment gave the floodwaters a dense, muddy character, increasing their ability to erode and transport material. As the current slowed in certain areas, this sediment settled, forming thick deposits that can still be studied today. Layers of sand and silt, sometimes many meters thick, mark the passage of the flood, preserving a record of how the water moved and where it paused or spread out. The temperature of the water would have been cold, fed by melting ice, yet the movement itself generated turbulence and mixing, creating complex currents within the flow. Icebergs and large chunks of ice carried along by the flood added another dimension to the movement, grinding against the banks and contributing to the erosion of the landscape. It is interesting to think about the sound of such an event. Standing near a large waterfall or a powerful river today, the noise of rushing water is loud enough to dominate the surroundings. A megaflood would have produced a continuous distant roar, audible across great distances, punctuated by the cracking of ice and the grinding of rocks carried in the current. The air itself may have been filled with mist and fine spray near constricted channels, and winds generated by temperature differences between water and land could have carried moisture far beyond the immediate flood zone. Despite the immense power of the flood, its progress across the continent was guided by the shape of the land. Valleys directed the flow, ridges slowed or diverted it, and the gradual slope of the terrain determined the general direction of the movement. Gravity remained the driving force, pulling the water toward lower elevations and eventually toward the oceans. One of the pathways taken by floodwaters from Lake Agassiz led southward through river systems that ultimately connected to the Gulf of Mexico. Another route, opened later as the ice retreated further, directed water eastward and northward toward the North Atlantic. Each pathway left its own pattern of erosion and sediment deposition, allowing scientists to reconstruct the sequence of events thousands of years later. The distance travelled by some of these floodwaters was enormous. Water released in the interior of the continent moved hundreds or even thousands of kilometres before reaching the sea. Along the way, it reshaped landscapes, altered river courses, and deposited sediments that remain part of the geological record. When water moves at that scale, it does not simply pass through an area and leave it unchanged. It transforms the ground it crosses. Channels deepen, new lakes form in scoured basins, and wetlands appear in low-lying regions where water lingers after the main current has passed. Over time, vegetation returns, animals recolonize, and the scars of the flood soften, but the underlying changes remain. The modern landscape of parts of North America still reflects the passage of these ancient waters, even though the events themselves are far beyond living memory. One of the most striking aspects of the megaflood is how it connects local events to global consequences. The release of such large volumes of fresh water into the oceans can alter salinity, which in turn affects ocean circulation. Currents that depend on differences in temperature and salt content may slow or shift when large amounts of fresh water are introduced. This connection between the flood and changes in climate is an important part of the story, and we'll look at it in detail as we continue. For now, it is enough to recognise that the movement of water from Lake Agassiz was not just a regional event. It was part of a chain of processes that extended far beyond the boundaries of the lake itself. It is also worth reflecting on how brief the period of active flooding may have been compared to the time it took for the lake to form. Centuries of melting and accumulation created the reservoir, but the most dramatic drainage events may have unfolded over months or years. In geological terms, that is an instant. This contrast between slow build-up and rapid release appears often in Earth's history. Volcanoes accumulate pressure over long periods before erupting. Fault lines store energy for centuries before an earthquake releases it in seconds. Lakes like Agassiz gather water gradually before releasing it in floods that reshape entire regions. As the waters moved outward, the level of the lake behind the breach steadily dropped. Shorelines retreated, exposing vast areas of former lake bed. Rivers that had once flowed gently into the lake now cut channels across newly exposed ground, establishing new drainage patterns that would persist long after the flood ended. The glacier itself continued to retreat, opening additional outlets and allowing the remaining water to find new pathways. The immense inland sea that had dominated the region for so long began to fragment into smaller lakes and wetlands, each a remnant of the larger whole. Yet the marks of the flood remained, written in valleys, sediments, and the contours of the land. Scientists studying these features can trace the routes taken by the water, estimating flow rates, and reconstructing the sequence of events with increasing precision. All of this evidence points to a period when water truly moved on a continental scale, not confined to rivers or coastlines, but sweeping across vast areas, reshaping the surface of the land and influencing the oceans beyond. Looking at a river today, even a large one, there is usually a sense that it fits within its valley, as though the land and the water have reached an understanding over long stretches of time. The banks guide the current shapes the banks, and the result is something balanced and familiar. What formed during the drainage of Lake Agassiz was very different. The channels carved by those floodwaters were so immense that calling them rivers feels almost misleading, because the scale of flow that created them far exceeded anything that normally defines a river at all. When scientists first began studying some of these valleys, they noticed something unusual. The channels were far too large for the streams now flowing through them. In many places, a modest river wound quietly along the floor of a valley, that stretched kilometres across. The mismatch was striking. A small modern current could not possibly have carved such a vast passage. Something much larger must have done the work. Those oversized valleys are among the clearest fingerprints left by the megafloods associated with Lake Agassiz. They appear as broad spillways, sometimes tens of kilometres wide, with steep sides and flat bottoms that suggest powerful, fast-moving water once filled them from edge to edge. The rivers that now occupy these valleys seem almost temporary by comparison, like narrow threads running along the floor of enormous corridors. To imagine what those flood channels looked like when they were active, it helps to picture not a single river, but a network of immense currents, branching and rejoining, spreading across low terrain, and then converging again as the land guided them toward lower elevations. Water did not politely remain within narrow banks. It occupied entire valleys, sometimes overtopping them, spilling across divides, and cutting new routes as it went. One of the reasons these flood channels became so large is the speed and volume of the flow. Water moving rapidly carries enormous energy, and that energy is transferred to the ground in the form of erosion. Sand and gravel suspended in the current act like grinding tools, wearing away rock and sediment. Larger stones roll and bounce along the bottom, carving grooves and potholes as they move. This process can reshape the land surprisingly quickly when the flow is powerful enough. Valleys deepen, banks collapse, and new channels form. In the case of Lake Agassiz, the sheer volume of water meant that these changes occurred on a scale rarely seen in Earth's recent history. Evidence of this erosion can still be found in the form of scoured bedrock surfaces, streamlined hills, and giant ripple marks left behind as sediment settled when the floodwaters slowed. Some of these ripple marks are so large that they can only be fully appreciated from the air, stretching for hundreds of meters between crests, silent reminders of currents that once moved with astonishing force. It is interesting to consider how different the soundscape of such a landscape would have been during the flood. A modern river produces a constant murmur or roar, depending on its size and speed. Multiply that many times over, and imagine the sound of water rushing through valleys miles wide, carrying ice, rocks, and sediment. The air would have vibrated with the continuous thunder of moving water, a sound that might have been heard far beyond the immediate flood zone. Yet despite the violence of the flow in certain areas, not all parts of the floodplain would have experienced the same intensity. Where the land was flat, the water spread out into broad, shallow sheets, moving more slowly but still carrying large amounts of sediment. These areas may have resembled temporary inland seas, their surfaces broken by low waves driven by wind and current. As the floodwaters advanced, they also interacted with existing rivers, sometimes overwhelming them entirely. Channels that had carried modest flows for centuries were suddenly filled with torrents far beyond their capacity. Banks eroded, floodplains were stripped of vegetation, and the courses of rivers were altered, sometimes permanently. One of the most striking consequences of such floods is the creation of what geologists call spillways. These are large channels formed when water overtops a divide and begins to flow along a new route. Once established, a spillway can carry enormous volumes of water, enlarging rapidly as erosion widens and deepens it. Several major spillways associated with Lake Agassiz have been identified, each marking a pathway taken by floodwaters at different times. Some directed water southward toward the Mississippi River system, others carried it eastward or northward as the ice retreated and new outlets became available. These shifting drainage routes are an important part of the story, because they show that the flood was not a single simple event. The lake drained in stages, sometimes catastrophically, sometimes more gradually, depending on the configuration of ice and land at the time. Sediments carried by the flood played a major role in shaping the downstream landscape. Fine clays and silt settled in quieter areas, forming thick layers that would later become fertile soils. Coarser materials like sand and gravel were deposited in bars and ridges, creating features that can still be seen in river valleys today. In some places, the floodwaters left behind large erratic boulders, rocks transported far from their original locations by the force of the current, or by ice carried within it. These boulders, sometimes resting alone in fields or forests, are another quiet clue to the immense power of the water that moved them. The interaction between floodwaters and vegetation would also have been dramatic. Forests and grasslands in the path of the flood were uprooted or buried under sediment. In the aftermath, new plant communities colonized the disturbed ground, beginning the long process of ecological recovery that follows large disturbances. It is easy to imagine such events as chaotic and destructive, and in many ways they were. Yet they also played a role in shaping landscapes that later supported life in new ways. Floodplains enriched with sediment became fertile regions. New lakes and wetlands formed in scoured basins. Rivers established new courses that would guide water and nutrients across the land for thousands of years. The legacy of those oversized rivers is still visible today, not only in the shape of valleys but also in the distribution of soils, wetlands and drainage patterns across large parts of North America. Modern maps of river systems often follow pathways first carved or enlarged by these ancient floods. Another fascinating aspect of these flood channels is how they help scientists estimate the scale of the events that created them. By measuring the size of valleys, the composition of sediments, and the characteristics of erosion features, researchers can calculate the flow rates required to produce such landforms. These calculations consistently point to discharges far beyond those of modern rivers. The study of these ancient channels has also provided insights into other megafloods around the world. Similar features have been found in regions affected by glacial outburst floods, and even on the surface of Mars, where enormous dry channels suggest that water once flowed there on a massive scale. Returning to the landscape shaped by Lake Agassiz, it is remarkable how quickly such immense rivers disappeared once the floodwaters subsided. As the lake level dropped and the outflow diminished, the vast channels were left largely empty. Smaller rivers eventually occupied some of them, but the scale of the original flow was never repeated. Over time, vegetation softened the starkness of the scoured land, sediment stabilized, and ecosystems returned. To someone walking through those valleys thousands of years later, there would be little to suggest that they had once carried torrents powerful enough to reshape the continent. Yet the evidence remains for those who know how to read it. The width of a valley, the layering of sediments, the presence of large ripple marks and erratic boulders all tell the story of water moving in quantities almost beyond imagination. Far downstream from the Great Lake, beyond the widening valleys and the enormous spillways, the floodwaters continued their long journey, guided by gravity and the shape of the land. What began as a release from an inland basin did not end in a nearby lowland or an isolated depression. The water kept moving, day after day, spreading through river systems, merging into larger channels, and eventually reaching the edges of the continent where land met sea. To appreciate what happened when the flood reached the oceans, it helps to picture the scale of the movement that preceded it. By the time the water approached the coastline, it had already travelled hundreds, sometimes thousands of kilometres. Along the way it had carved valleys, deposited vast sheets of sediment, and altered existing rivers. Yet even after such a long journey, the volume of water remained immense. When fresh water on that scale enters the ocean, it does not simply disappear into the surrounding salt water. It spreads, forming large plumes that can extend far from the point of entry. Because fresh water is less dense than salt water, it tends to remain near the surface, flowing outward in broad layers before gradually mixing. In the case of Lake Agassiz, scientists believe that at least some of the largest outbursts directed water toward the North Atlantic. The exact routes varied over time as glaciers retreated and new drainage pathways opened, but the result was the same. Enormous pulses of fresh water entering an ocean whose circulation depends on the balance between temperature and salinity. Ocean currents are driven in part by differences in density. Cold, salty water is heavier than warm, fresh water, and this difference helps drive a global system of circulation sometimes called the thermohaline circulation. In the North Atlantic, one of the key processes involves cold, salty surface water becoming dense enough to sink, helping to pull warmer water northward from lower latitudes. This circulation acts like a vast conveyor belt, redistributing heat around the planet. It is one of the reasons that parts of Europe, for example, are milder than other regions at similar latitudes. Introducing large amounts of fresh water into this system can disrupt it. Freshwater dilutes the salt content of surface water, making it less dense and less likely to sink. If enough fresh water is added, the process of deep water formation can slow or even pause, altering the flow of currents and the distribution of heat. Evidence suggests that such a disruption may have occurred during the period known as the Younger Dryas, a sudden return to colder conditions in parts of the Northern Hemisphere roughly 12,000 years ago. Ice cores, sediment records, and other climate proxies indicate that temperatures dropped sharply in some regions, interrupting the general warming trend that marked the end of the Ice Age. Many scientists think that the drainage of Lake Agassiz played a role in triggering or amplifying this cooling. The sudden influx of fresh water into the North Atlantic may have weakened ocean circulation, reducing the transport of warm water northward and allowing cold conditions to take hold. It is important to note that this connection is still studied and debated, because the climate system is complex and multiple factors were likely involved. Even so, the timing of the major drainage events and the onset of cooling episodes suggest that the floodwaters from Lake Agassiz were not merely a regional event. They were part of a chain of processes that affected the entire planet. Imagining the meeting of floodwater and ocean helps bring this into focus. At the mouth of a great river today, the water often carries sediment that clouds the sea for kilometers offshore. During the drainage of Lake Agassiz, the plume of fresh water would have been far larger, spreading across vast areas of the ocean surface. Sediments carried by the flood settled gradually to the seafloor, forming layers that scientists can now examine to reconstruct the timing and magnitude of these events. Changes in the chemical composition of marine sediments, including shifts in isotopes and microfossil assemblages, provide clues about how salinity and temperature changed during and after the influx of fresh water. These records are like pages in a history book written in mud and microscopic shells, each layer preserving a snapshot of conditions at the time it formed. The arrival of so much fresh water would also have affected marine ecosystems. Many ocean organisms are sensitive to changes in salinity and temperature, and sudden shifts can alter the distribution of species. Plankton communities in particular respond quickly to environmental changes, and their remains in sediment cores provide valuable evidence of past conditions. Closer to shore, the floodwaters may have reshaped coastal landscapes as well. Deltas expanded, channels shifted, and low-lying areas were inundated. The boundary between river and sea is always dynamic, but the scale of the discharge from Lake Agassiz would have amplified those changes. It's also worth considering how the floodwaters, cold and sediment-laden, would have looked as they entered the ocean. The colour difference alone might have been striking. Plumes of pale, cloudy water spreading into darker, saltier seas, currents carrying floating debris and ice far from the coastline. Over time, mixing would have blurred these boundaries, but during the initial stages the contrast could have been visible over large distances. One of the remarkable aspects of this story is how interconnected Earth's systems are. A lake forming in the interior of a continent, held in place by ice, eventually released water that may have altered ocean currents thousands of kilometers away. That change in ocean circulation in turn affected climate patterns across large parts of the globe. It is a reminder that events in one region can ripple outward in ways that are not immediately obvious, linking distant places through the movement of air and water. The Younger Dryas cooling, if influenced by these floods, was not a brief anomaly lasting only a few years. It persisted for more than a millennium in some regions, a significant interval in human terms, though still relatively short on geological timescales. During that period, glaciers in some areas advanced again, vegetation patterns shifted, and human populations adapted to changing conditions. Eventually, warming resumed, and the long transition out of the Ice Age continued. Meanwhile, the remnants of Lake Agassiz continued to drain as the glacier retreated further and new outlets opened. What had once been a vast inland sea fragmented into smaller lakes and wetlands, many of which still exist today in altered form. The Red River, Lake Winnipeg, and other modern waterways and lakes occupy parts of the former basin, their presence a quiet reminder of the immense body of water that once dominated the region. Looking at a map of these areas today, it is not immediately obvious that they were once part of a single, enormous lake. Only by studying the sediments, the ancient shorelines, and the patterns of drainage does the full picture emerge. It is interesting to reflect on how the land remembers events long after the water is gone. Valleys remain carved, sediments remain layered, and coastlines bear the subtle signatures of past sea level and salinity changes. The flood itself lasted only a short time compared to the ages of the Earth, but its effects were written into landscapes and oceans in ways that persist to this day. Another aspect worth considering is the sheer energy involved in moving such volumes of water. The gravitational potential energy stored in a lake the size of Agassiz, raised above sea level and held back by ice, is enormous. When released, that energy is converted into motion, erosion, and heat, driving the processes that carved channels and transported sediments across continents. In many ways, the flood was an expression of gravity working on a grand scale, the same force that causes rain to fall and rivers to flow, amplified by the size of the reservoir and the height from which the water descended. Standing on a quiet shoreline today, watching waves lap gently against the land, it can be difficult to imagine that the same element, water, can move with such power. Yet the history of Lake Agassiz shows that under the right conditions, water can reshape continents and influence climates far beyond its point of origin. As the floodwaters finally dispersed into the oceans and the lake basin continued to drain, the landscape entered a new phase. Rivers established more stable courses, vegetation spread across exposed lake beds, and ecosystems adapted to the changing environment. Long after the waters had begun their journey away from the Great Basin, the effects of their release were still unfolding, not only in the reshaped valleys and new shorelines, but in the atmosphere and oceans themselves. The flood was not simply a geological event, it was part of a much larger chain of changes that reached far beyond the land where the lake had once existed. To understand what followed, it helps to picture the climate of the Earth at that time. The world had been warming gradually as the last ice age loosened its grip. Glaciers were retreating, forests were spreading into regions that had been tundra, and temperatures in many parts of the northern hemisphere were rising. It was not a smooth or perfectly steady warming, but the overall direction was clear. The long cold period was ending. Then, quite abruptly in geological terms, that warming slowed, paused, and in many places reversed. Temperatures in parts of North America and Europe dropped noticeably. Glaciers that had been retreating stabilized or even advanced slightly. Vegetation patterns shifted, with cold-adapted species returning to areas where warmer conditions had begun to take hold. This interval, known today as the Younger Dryas, lasted for more than 1,000 years before warming resumed once again. The cause of this sudden chill has been studied for decades, and while the full story is complex, many researchers believe that the drainage of Lake Agassiz played a significant role. The key lies in the way freshwater interacts with the oceans, particularly in the North Atlantic. Ocean circulation is not driven only by winds and tides. A major part of the system depends on differences in temperature and salinity, which together determine the density of seawater. In the North Atlantic, cold, salty water becomes dense enough to sink, forming deep currents that help pull warmer surface water northward from lower latitudes. This movement of heat helps moderate climates, especially in regions bordering the Atlantic. When large amounts of fresh water enter this system, the balance changes. Fresh water is less dense than salt water, so it tends to remain near the surface, forming a layer that resists sinking. If that layer becomes thick enough, it can slow or disrupt the formation of deep currents, reducing the flow of warm water toward higher latitudes. The floodwaters from Lake Agassiz, cold and fresh, may have spread across the surface of the North Atlantic in enormous plumes. Over time, these plumes mixed with the surrounding ocean, but the immediate effect would have been a reduction in salinity in key regions where deep water formation normally occurs. Scientists study this process by examining cores taken from the ocean floor. These cores contain layers of sediment that accumulate year after year, preserve in tiny shells of marine organisms and chemical signatures that reveal past conditions. Changes in the composition of these layers provide evidence of shifts in temperature and salinity that coincide with the timing of major freshwater inputs. Ice cores drilled from Greenland offer another line of evidence. These cores preserve a record of atmospheric conditions in layers of compressed snow and ice, allowing researchers to track temperature changes over tens of thousands of years. In these records, the onset of the Younger Dryas appears as a sharp drop in temperature, occurring over a relatively short period. It's remarkable to think that a lake draining far inland could contribute to such a widespread climatic shift. Yet the Earth's systems are deeply interconnected. Oceans, atmosphere, ice, and land all influence one another, sometimes in ways that are not immediately obvious. The cooling associated with the Younger Dryas was not uniform everywhere. Some regions experienced more dramatic temperature changes than others. In parts of Europe, the return to colder conditions affected vegetation and animal populations, altering the environments in which early human communities lived. In North America, the climate also cooled, though the exact patterns varied from region to region. For people living at that time, these changes would not have been perceived as a sudden event in the way we think of a storm or an earthquake. Instead, they would have noticed that winters were becoming harsher again, that growing seasons were shorter, and that familiar patterns of weather were shifting. Over years and decades, these changes would have shaped migration routes, hunting patterns, and the availability of resources. One of the interesting aspects of the Younger Dryas is how quickly it began and ended compared to many other climate changes. Geological records suggest that the transition into the colder period may have occurred within a few decades in some regions, a remarkably short time on the scale of Earth's history. The end of the Younger Dryas, when warming resumed, also appears to have been relatively rapid. The sensitivity of the climate system to relatively small triggers is something scientists continue to study carefully, because it has implications for understanding how modern climate might respond to changes in ocean circulation or freshwater input from melting ice sheets. Returning to the ancient flood, it is important to remember that Lake Agassiz did not drain in a single event. Multiple drainage episodes likely occurred as the glacier retreated and new outlets opened. Each episode may have delivered pulses of fresh water to the oceans, contributing to the overall effect on circulation. The timing of these pulses and their exact volumes are still subjects of ongoing research. New data from sediment cores, improved dating techniques, and advances in climate modelling continue to refine our understanding of what happened. What is clear, however, is that the Earth's climate system can respond strongly to changes in freshwater input, particularly in regions where ocean currents play a crucial role in distributing heat. Another factor to consider is the presence of sea ice. Colder conditions in the North Atlantic would have allowed sea ice to expand, reflecting more sunlight back into space and reinforcing the cooling. This feedback loop, where cooling leads to more ice, and more ice leads to further cooling, may have helped sustain the Younger Dryas for centuries. Atmospheric circulation patterns also shifted during this period, altering precipitation and temperature in various parts of the world. Some regions became drier, others wetter, as the balance of winds and pressure systems adjusted to the cooler North Atlantic. It is fascinating to think about how a sequence of events beginning with the slow melting of a glacier could eventually influence weather patterns thousands of kilometers away. The story of Lake Agassiz is not just about water moving across land. It is about the way Earth systems are connected, each part influencing the others in a continuous exchange of energy and matter. Despite the cooling, life continued to adapt. Plants and animals shifted their ranges, following the climates to which they were best suited. Human populations adjusted as well, altering their movements and ways of living in response to changing conditions. Eventually, the Younger Dryas came to an end. Temperatures began to rise again, glaciers resumed their retreat, and the long transition into the warmer climate of the present interglacial period continued. The causes of this warming are still studied, but it likely involved a combination of changes in ocean circulation, atmospheric composition, and the gradual influence of Earth's orbital cycles. By this time, the remnants of Lake Agassiz were shrinking. The glacier that had once dammed its waters was retreating farther north, and new drainage routes allowed the remaining water to flow away more steadily. The immense inland sea that had dominated central North America was giving way to smaller lakes, rivers, and wetlands. Yet the memory of the flood remained, written in sediments, landforms, and the chemical signatures preserved in ice and ocean cores. These records allow scientists to reconstruct the sequence of events with increasing detail, revealing how closely linked the Earth's systems truly are. It is also worth reflecting on how delicate some of these balances can be. Ocean currents depend on differences in temperature and salinity that may seem small in absolute terms, yet they drive circulation patterns affecting entire continents. A sudden influx of fresh water can tip that balance, setting off a cascade of changes that ripple through the climate system. This understanding has practical importance today, as modern glaciers and ice sheets continue to melt in response to warming temperatures. While the conditions are different from those at the end of the Ice Age, the principles governing ocean circulation and freshwater input remain the same. Looking back at the time of Lake Agassiz, it becomes clear that the flood was not an isolated event. It was part of a larger transition, a period when the planet was emerging from one climatic state and moving toward another. The sudden chill of the Younger Dryas was one of the final echoes of the Ice Age, a reminder that the path from cold to warm was not perfectly smooth. As the climate stabilized and warming resumed, ecosystems expanded, glaciers retreated further, and the landscapes shaped by the flood continued to evolve. Rivers carved new channels through the sediments left behind, and vegetation spread across the former lake bed, gradually transforming it into the fertile plains and forests seen today. In the quiet of those changing landscapes, the evidence of the flood remained, subtle but persistent, waiting to be discovered thousands of years later by those who would study the land and wonder how such immense forces had once been set in motion. Freshwater seems gentle when we encounter it in everyday life. It falls as rain, gathers in quiet ponds, flows in streams that wind through forests and fields. Even large lakes often appear calm, their surfaces disturbed only by wind or the passing of a boat. Yet when fresh water is stored in enormous quantities and then released or redistributed, it can influence systems that operate on a planetary scale. The story of Lake Agassiz is one example of that, but it also serves as a window into a broader principle. Water, especially fresh water, plays a powerful role in shaping climate, oceans, and the living world. To understand why, it helps to begin with a simple idea. The oceans are not uniform. Their waters differ in temperature, salinity, and density, and those differences drive movement. Warm water tends to remain near the surface, while colder, denser water sinks. Salt increases density, so saltier water sinks more readily than fresher water at the same temperature. These relationships create a complex circulation system that connects the world's oceans, moving heat and nutrients across vast distances. This circulation is sometimes compared to a slow-moving conveyor, though in reality it is far more intricate than any mechanical system. Currents branch, merge, and change direction under the influence of winds, coastlines, and the rotation of the Earth. Still, one of the key engines of this system lies in the North Atlantic, where cold, salty water becomes dense enough to sink, drawing warmer water northward near the surface. Now imagine what happens when a large volume of fresh water enters that region. Fresh water dilutes the salt content of the ocean surface, making the water less dense. If the dilution is strong enough, the surface water may no longer sink as readily, and the entire circulation pattern can weaken or shift. This is not merely a theoretical possibility. Evidence from the end of the last ice age suggests that such changes have occurred in the past, and that they may have been linked to sudden climate shifts like the Younger Dryas. When Lake Agassiz released vast amounts of fresh water into the ocean, the balance of salinity in parts of the North Atlantic may have been altered enough to slow the currents that carried heat northward. A slower circulation means less heat transported to higher latitudes. Over time, that reduction can lead to cooler conditions, changes in weather patterns, and shifts in ecosystems. The cooling associated with the Younger Dryas affected large areas, demonstrating how a regional event, the drainage of a lake, could ripple outward to influence climate across continents. Fresh water can affect the planet in other ways as well. Large lakes and ice sheets act as reservoirs, storing water that would otherwise contribute to sea level. When those reservoirs shrink, whether through melting or drainage, the water eventually reaches the oceans, raising sea levels. At the end of the Ice Age, melting glaciers and the release of water from proglacial lakes contributed to a significant rise in global sea level, reshaping coastlines around the world. Shorelines that had once been far from the sea were gradually submerged. Low-lying plains became coastal wetlands or shallow seas. Human populations living near coasts would have had to adjust to these changes, moving inland as the water advanced over generations. Freshwater also plays a crucial role in ecosystems. Rivers carry nutrients from the land to the sea, supporting marine life in coastal regions. Floods deposit fertile sediments on floodplains, enriching soils and encouraging plant growth. Wetlands formed by freshwater provide habitat for countless species, from birds and fish to insects and amphibians. When the drainage of a lake as large as Agassiz occurred, it did not simply deliver water to the ocean. It carried enormous quantities of sediment and nutrients as well. These materials influenced the chemistry of coastal waters, potentially affecting productivity in marine ecosystems. Another important effect of freshwater involves the formation and melting of sea ice. Freshwater freezes at a slightly higher temperature than saltwater, and layers of fresher water at the ocean surface can encourage ice formation during cold periods. Increased sea ice reflects more sunlight, which can reinforce cooling by reducing the amount of solar energy absorbed by the ocean. This feedback loop, where cooling leads to more ice, and more ice leads to further cooling, is one reason climate shifts can sometimes intensify once they begin. The introduction of fresh water into the North Atlantic during the Younger Dryas may have contributed to such feedbacks, helping sustain cooler conditions for centuries. Freshwater also influences atmospheric circulation. Changes in ocean temperature affect the distribution of heat in the atmosphere, which in turn alters wind patterns and precipitation. Regions that depend on certain weather systems may experience shifts in rainfall or seasonal temperatures when ocean currents change. Looking at the present day, scientists study modern freshwater inputs from melting glaciers and ice sheets to understand how similar processes might unfold in the future. The Greenland ice sheet, for example, is losing ice at an increasing rate, adding fresh water to the North Atlantic. While the volumes involved are smaller than those released during the drainage of Lake Agassiz, they are large enough to be monitored carefully because of their potential impact on ocean circulation. One of the remarkable aspects of Earth's climate system is how interconnected it is. A change in one region can propagate through oceans and atmosphere to affect distant places. This interconnectedness is sometimes difficult to appreciate because the links are not always obvious. A lake draining in the interior of a continent might not seem related to temperatures in Europe or storm patterns in the Atlantic, yet through the movement of water and heat, such connections exist. It is also worth remembering that fresh water is part of a continuous cycle. Water evaporates from oceans, falls as rain or snow, flows through rivers and lakes, and eventually returns to the sea. This hydrological cycle operates constantly, shaping landscapes and sustaining life. During the Ice Age, a significant portion of Earth's fresh water was locked in ice sheets. As those ice sheets melted, the redistribution of that water altered sea levels, ocean circulation and climate patterns. Lake Agassiz was one of the many reservoirs that temporarily stored meltwater before releasing it back into the global system. Thinking about water in this way can change how we see familiar landscapes. A quiet river may appear stable, yet it is part of a network that connects mountains to oceans, atmosphere to soil. A lake may seem permanent, yet over thousands of years it can grow, shrink, or vanish entirely as climates shift and landforms change. In the case of Lake Agassiz, the release of fresh water was dramatic enough to leave clear traces in geological and climatic records. But smaller scale examples occur all the time. Seasonal snowmelt influences river flows and ecosystems. Floods reshape valleys and deposit fertile soils. Even the slow melting of mountain glaciers affects water supplies for millions of people. The difference with megafloods is one of scale. When the volumes involved become large enough, the effects extend far beyond the immediate area. Rivers become temporary seas, coastlines change, and the chemistry of oceans shifts. There is something humbling about considering how a substance as familiar as water can have such far-reaching effects. We encounter it daily, drink it, wash with it, watch it fall from the sky. Yet under certain conditions, it becomes a force capable of altering climate and reshaping continents. Another aspect worth considering is the timescale over which these changes occur. The drainage of Lake Agassiz may have taken place over months or years, but the climatic effects lasted centuries. The sediments deposited by the flood remain visible thousands of years later. The landscapes shaped by those waters continue to influence rivers, soils, and ecosystems today. This layering of timescales is a common feature of Earth systems. Short events leave long-lasting marks. A storm may pass in hours, yet the trees it uproots and the sediments it moves can shape a landscape for decades. A flood may last days, yet the valleys it carves endure for millennia. Fresh water, moving through the hydrological cycle, connects these timescales. It falls as rain in moments, flows through rivers over days, fills lakes over centuries, and shapes climates over millennia. Returning to the ancient flood, it becomes clear that its significance lies not only in the drama of the water's release, but also in the broader processes it reveals. It shows how sensitive the climate system can be to changes in freshwater distribution. It illustrates the power of water to reshape land and influence oceans, and it reminds us that events in one part of the planet can have consequences far beyond their point of origin. Across large parts of central North America, the land still carries quiet reminders of what happened when the waters of Lake Agassiz were released. At first glance, many of these places appear ordinary. Fields stretch to the horizon, rivers move slowly through wide valleys, and small towns sit on ground that feels stable and unremarkable. Yet beneath that calm surface lies a record of powerful forces, written in the shapes of valleys, the layers of soil, and the subtle patterns of elevation that only become obvious when you know what to look for. One of the most striking features left behind by the ancient lake is the remarkable flatness of certain regions that were once part of its basin. The Red River Valley, for example, is so level that changes in elevation over many kilometres can be measured in only a few metres. This flatness is not accidental. It is the result of fine sediments settling slowly to the bottom of a vast body of still water. Over centuries, layer upon layer of silt and clay accumulated, smoothing the underlying landscape until it resembled the floor of a shallow bowl. When the lake drained and the water receded, that flat lake bed was left exposed. Over time, grasses and other plants took root, soils developed, and eventually people began to farm the land. Today, the fertility of these soils is well known, but their origin is sometimes easy to overlook. Every field in such regions is, in a sense, part of the former floor of an inland sea. The shorelines of Lake Agassiz also left enduring marks. Waves driven by wind along the edges of the lake built ridges of sand and gravel, much like the beaches we see today, along the edges of smaller lakes and oceans. As the water level rose and fell over time, new shorelines formed at different elevations, leaving behind a series of parallel ridges that trace the changing extent of the lake. These beach ridges can still be found stretching across the landscape, sometimes visible as low, winding rises that run for many kilometres. To someone unaware of their origin, they might look like natural embankments or gentle hills, but from above, their patterns reveal their true nature, long arcs marking where waves once broke against the land thousands of years ago. In some areas, these ancient shorelines are so well preserved that it is possible to trace the outlines of the lake at different stages of its history. Each ridge represents a period when the water stood at a particular level, long enough for waves to shape the shore. By studying these ridges and dating the sediments within them, scientists can reconstruct how the lake expanded and contracted over time. Beyond the former basin itself, the scars left by the flood become more dramatic. The spillways carved by the escaping water remain some of the most impressive features in the landscape. These channels, often far larger than any modern river, cut through hills and across plains. Their size a testament to the immense flows that once passed through them. Standing at the edge of one of these spillways today, it can be difficult to imagine the scale of the water that created it. The valley may be kilometres wide, with steep sides and a flat floor now covered in vegetation. A modest river may wind along the bottom, seeming almost out of place in such a vast space. Yet the dimensions of the valley tell a clear story. Only a flood of extraordinary magnitude could have carved such a feature. Another type of evidence appears in the form of giant ripple marks preserved in sediments. When water flows rapidly over sand or gravel, it can create ripples on the bed of the channel. In ordinary streams, these ripples are small, perhaps a few centimetres high. But in megaflood conditions, the ripples can grow to astonishing sizes, with crests several metres high and spaced tens of metres apart. These giant ripples have been found in regions affected by ancient floods, their patterns still visible from the air. They are silent records of currents moving at speeds and depths far beyond anything seen in modern rivers. Each ripple marks the movement of sediment under powerful flow, frozen in place when the water receded. Scoured bedrock provides another clue. In places where the floodwaters were especially strong, the moving water and sediment stripped away soil entirely, exposing the underlying rock. The surfaces of these rocks often bear scratches and grooves, carved by stones dragged along by the current. Some areas even show smooth, polished surfaces where abrasion by sediment-laden water wore the rock down over time. Potholes drilled into bedrock are another striking feature. These form when swirling currents trap stones in small depressions, causing them to rotate and grind against the rock beneath. Over time, the motion enlarges the depression into a circular hole, sometimes several metres deep. Such potholes are found in regions known to have experienced megafloods, clear evidence of the intense turbulence that once existed there. Farther downstream, thick deposits of sand and gravel mark areas where the floodwaters slowed and dropped the sediments they were carrying. These deposits often form terraces or bars that rise above modern floodplains, indicating the height and extent of the ancient flows. By studying the size and arrangement of these sediments, scientists can estimate the speed and depth of the water that transported them. Erratic boulders provide yet another line of evidence. These large rocks, sometimes weighing many tons, were carried by the floodwaters or by icebergs within them and deposited far from their original locations. Finding such boulders resting on terrain that could not have produced them locally is a clear sign that powerful forces moved them there. In addition to these physical features, the structure of soils across the region reveals the history of the lake and its drainage. Layers of fine clay deposited in still water lie beneath coarser sediments left by later floods and river activity. By examining these layers, geologists can piece together a timeline of events, identifying periods when the lake was stable, when it drained rapidly, and when rivers began to reshape the landscape afterward. The land also preserves subtler signs of change. Drainage patterns in some areas still reflect the pathways carved or enlarged by the floodwaters. Rivers follow courses determined thousands of years ago, guided by valleys that owe their shape to ancient currents. Wetlands occupy depressions scoured by the flood, their quiet waters a gentle contrast to the torrents that once shaped them. Vegetation patterns can also hint at the past. Soils formed from lake sediments often differ from those developed on glacial till or bedrock, supporting different types of plant communities. In some regions, the boundary between former lake bed and surrounding terrain can be traced by changes in vegetation, as well as elevation. It is remarkable how much of this evidence has survived despite the passage of thousands of years. Wind, rain, and the activities of plants and animals gradually soften the sharp edges of landforms, yet the larger patterns remain. Valleys do not disappear quickly, and thick sediment deposits persist long after the waters that laid them down are gone. Modern technology has made it easier to recognize these features. Satellite imagery and aerial photography reveal patterns that are difficult to see from the ground, such as the sweeping curves of ancient shorelines or the full extent of giant ripple fields. Digital elevation models allow scientists to map subtle changes in terrain, identifying former channels and terraces with great precision. These tools have transformed our understanding of Lake Agassiz and its floods, allowing researchers to reconstruct the history of the lake in increasing detail. What was once inferred from scattered observations can now be seen across entire regions, the marks of the flood forming a coherent picture when viewed from above. There is something quietly compelling about landscapes that carry such memories. Walking across a flat plain that was once the bottom of a lake, or standing in a valley carved by water far greater than any river now present, invites a kind of reflection. The land seems stable and permanent, yet it has changed dramatically in the past and will continue to change in the future. These reminders are not limited to North America. Around the world, landscapes bear the marks of ancient floods, volcanic eruptions, glacial advances, and other events that reshape the surface of the planet. Each scar tells a story, and together they reveal how dynamic Earth has always been. In the case of Lake Agassiz, the scars are both vast and subtle. Some are obvious, like the enormous spillways and terraces. Others are gentle, like the faint ridges of ancient beaches or the fine-grained soils beneath modern fields. All of them are pieces of a larger narrative, one that connects the retreat of ice sheets, the movement of water, and the shifting of climate. It is also worth considering how recent these events are in geological terms. 12,000 years may seem like a very long time from a human perspective, yet on the scale of Earth's history it is a brief interval. Many of the features left by the flood are still sharp and well preserved, because there has not been enough time for erosion to erase them completely. As the centuries passed after the drainage of the lake, ecosystems gradually returned to the affected regions. Plants colonized exposed sediments, animals followed, and rivers established stable channels. Over time, the landscape settled into a new balance, shaped by processes that were slower and less dramatic than the flood itself. But the memory of that flood remains, not in written records or oral traditions, but in the contours of the land. The ground itself holds the story, waiting for those who know how to read it. From these physical traces, scientists have been able to reconstruct not only the existence of Lake Agassiz, but also the sequence of events that led to its formation, growth, and eventual drainage. The evidence scattered across plains, valleys, and coastlines fits together like pieces of a puzzle, revealing a picture of water moving on a scale that reshaped an entire continent. Piecing together an event that no human witnessed, one that happened thousands of years ago and lasted only a short time compared with the ages of the Earth, requires patience and a kind of quiet detective work. The story of the Lake Agassiz floods was not discovered all at once. It emerged gradually as scientists began noticing clues scattered across landscapes, rivers, sediments, and even the ocean floor. Each clue by itself might have seemed minor, but together they formed a consistent picture of a lake that once existed, and floods that reshaped vast regions. One of the first and most obvious clues came from the land itself. Early geologists travelling across parts of central North America noticed broad, flat plains with remarkably fine soils. These areas lacked the uneven terrain typical of glacial deposits, and instead resembled the bottoms of dried lakes. The flatness was so striking that it raised questions about how such a surface could have formed over such a wide area. Closer inspection revealed layers of clay and silt arranged in thin, regular bands. These sediments are characteristic of quiet water, where fine particles settle slowly to the bottom. In lakes, seasonal changes often produce alternating layers of slightly different composition, sometimes visible as faint stripes. By studying these layers, scientists realized that the plains had once been submerged beneath a large body of water that persisted for centuries. Ancient shorelines provided another important piece of evidence. In some regions, long ridges of sand and gravel traced gentle arcs across the landscape. These ridges resembled the beaches of modern lakes, but they lay far from any present shoreline and sometimes occurred at multiple elevations. This suggested that the water level had changed over time, leaving behind a sequence of former shorelines. Mapping these ridges revealed that they formed parts of a vast, interconnected system, outlining the shape of a single enormous lake rather than many small ones. As more ridges were identified and mapped, the scale of Lake Agassiz began to emerge. Understanding how the lake drained required a different set of clues. Scientists studying river valleys downstream from the former basin noticed channels that were far too large for the rivers flowing through them today. Some valleys were kilometres wide, yet contained only modest streams. Others showed signs of intense erosion, including scoured bedrock and large deposits of gravel and sand. These features indicated that powerful flows of water had once moved through those valleys. By measuring the size of the channels and the sediments within them, researchers could estimate the volume and speed of the water required to create them. The results pointed to floods of extraordinary magnitude, far beyond the scale of normal river activity. Sediment deposits offered additional insights. When floodwaters slow, they drop the material they're carrying, forming layers that can be studied long afterward. In many areas affected by the drainage of Lake Agassiz, thick sequences of sand and silt mark the passage of floodwaters. These layers often contain structures such as crossbedding and ripple marks that reveal the direction and strength of the currents that formed them. Dating these sediments was essential for determining when the floods occurred. Scientists used several methods to establish ages, including radiocarbon dating of organic material buried within the sediments and optically stimulated luminescence dating, which measures the last time mineral grains were exposed to sunlight. These techniques allow researchers to place the events within a timeline and compare them with other records, such as climate changes seen in ice cores. Evidence from the ocean floor has also played a key role. Cores taken from sediments in the North Atlantic contain layers that correspond to periods of increased freshwater input. Changes in the types of microscopic organisms preserved in these sediments indicate shifts in salinity and temperature, consistent with large pulses of fresh water entering the ocean. By comparing the timing of these oceanic changes with the dates of flood deposits on land, scientists have been able to link the drainage of Lake Agassiz to broader climatic events. This connection strengthens the case that the floods influenced ocean circulation and climate. Ice cores drilled from Greenland provide another valuable record. Each layer of ice represents a year of snowfall, preserving information about temperature and atmospheric composition. Within these cores, abrupt changes in temperature coincide with periods when freshwater inputs to the North Atlantic are believed to have occurred. The alignment of these independent records, land sediments, ocean cores and ice cores, provides a coherent picture of the timing and impact of the floods. Modern technology has made it possible to study these features in ways that were unimaginable a century ago. Satellite imagery allows scientists to identify ancient shorelines, spillways, and sediment patterns across entire regions. From above, the outlines of former lake beds and flood channels become much clearer, revealing patterns that are difficult to recognize from ground level. Digital elevation models created using data from satellites and airborne lasers can detect subtle changes in terrain, mapping the gentle slopes and ridges left behind by ancient shorelines or the channels carved by floodwaters. These maps help researchers reconstruct how water moved across the landscape and how the lake's size and shape changed over time. Computer models also play an important role in understanding the floods. By simulating the behavior of water flowing through channels of known dimensions, scientists can estimate how quickly the lake might have drained and how much water was released during different events. These models incorporate information about the topography of the land, the volume of the lake, and the likely characteristics of the ice dams that held it in place. Such simulations do not provide exact answers, but they help test whether proposed scenarios are consistent with the physical evidence. If a model predicts erosion patterns or sediment deposits that match what is observed in the field, it strengthens confidence in the reconstruction. Fieldwork remains an essential part of the process. Geologists and geomorphologists travel to remote locations to examine outcrops, measure sediment layers, and collect samples. Standing in a spillway or on an ancient shoreline, they look for details that reveal how the water behaved, the direction of flow, the energy of the current, and the sequence of events that shaped the land. Sometimes the clues are small. A layer of fine silt between two layers of sand may indicate a brief pause in flooding. A change in grain size may show where the current slowed or accelerated. Each observation adds another piece to the puzzle. It is interesting to reflect on how much of this work depends on careful observation and patience. The evidence is not always dramatic or obvious. Often it is subtle, requiring attention to patterns and relationships that only become clear when viewed in context. Another line of evidence comes from studying the rebound of the land after the ice sheets melted. By measuring how the crust has risen over time and mapping the tilt of ancient shorelines, scientists can estimate the weight of the ice and the timing of its retreat. This information helps reconstruct the shape of the basin that held Lake Agassiz and the pathways that became available for drainage as the glacier receded. All of these methods, sediment analysis, mapping of landforms, dating techniques, ocean and ice core studies, and computer modelling, work together to build a coherent picture of the past. No single piece of evidence tells the whole story, but when many independent lines of evidence point in the same direction, confidence in the reconstruction grows. One of the remarkable aspects of this work is that it continues to evolve. New technologies, such as improved satellite sensors and more precise dating methods, allow scientists to refine their understanding of the floods. Questions that were once difficult to answer are now being revisited with new data and new approaches. For example, researchers are still studying exactly how many major drainage events occurred, how quickly the largest floods unfolded, and how much fresh water entered the oceans during each episode. These details matter for understanding not only the history of Lake Agassiz, but also the sensitivity of the climate system to sudden changes. The process of reconstructing the flood is also a reminder of how landscapes preserve information over long periods. Valleys, sediments, and shorelines act as natural archives, recording events in forms that can be read long after the water has gone. Walking across a flat plain that was once a lake bed, or standing in a valley carved by ancient floodwaters can feel ordinary at first, yet the shapes of the land hold stories stretching back thousands of years. With the right tools and knowledge, those stories can be uncovered, revealing how dramatically the world has changed in the past. The reconstruction of Lake Agassiz and its floods is not just a tale of geological curiosity. It provides insight into how natural systems respond to large inputs of fresh water, how climate can shift abruptly, and how interconnected the Earth's systems truly are. Long before Lake Agassiz formed and long after its waters drained away, Earth experienced other floods of extraordinary size. These events were rare, separated by thousands or millions of years, but they shared certain patterns. Each involved a large body of water held back by natural barriers, each ended with a sudden release, and each left behind landscapes that still carry the marks of immense moving water. One of the most well-known examples took place in what is now the northwestern United States near the end of the last ice age. There, a vast body of water known as Glacial Lake Missoula formed when an ice sheet blocked a mountain valley. Like Lake Agassiz, this lake grew gradually as meltwater accumulated behind an ice dam. And like Agassiz, the barrier eventually failed. When Lake Missoula drained, it did not do so just once. Evidence suggests that the ice dam reformed and failed repeatedly, producing a series of enormous floods over thousands of years. Each flood sent torrents of water racing across eastern Washington, carving deep channels into basalt bedrock and leaving behind a landscape now known as the channeled scablands. If you look at aerial images of that region today, the marks of those floods are unmistakable. Vast dry channels, giant ripple marks, and isolated hills shaped like teardrops all point in the direction of the ancient currents. These features are so large that they are difficult to appreciate from the ground. Only from above does the full pattern become clear, showing how water once moved across the land with tremendous force. What makes the Missoula floods especially interesting is how controversial they once were. When geologist J. Harlan Bretz first proposed in the early 20th century that such immense floods had shaped the landscape, many scientists were skeptical. The idea of catastrophic floods on that scale seemed too dramatic, too far removed from the gradual processes that geology had traditionally emphasized. Over time, however, evidence accumulated. Sediment layers, shorelines of the ancient lake, and the discovery of giant ripple marks all supported Bretz's interpretation. Eventually, the scientific community accepted that megafloods had indeed occurred, reshaping the understanding of how landscapes can form. This shift in thinking also helped scientists recognize similar features in other parts of the world, including those associated with Lake Agassiz. Another remarkable flood occurred much earlier in Earth's history, at the end of the last glacial period in the region that is now the Black Sea. Some researchers have proposed that rising sea levels in the Mediterranean eventually breached a natural barrier at the Bosporus, allowing seawater to rush into what had been a lower freshwater basin. According to this hypothesis, the inflow may have been rapid enough to flood large areas of land, transforming the landscape and possibly influencing human populations living nearby. The details of this event are still debated, but sediment cores from the Black Sea show clear evidence of a transition from freshwater to marine conditions, indicating that a major change in water flow occurred. Even larger floods have taken place in earlier geological eras. During the late Miocene, about 5 million years ago, the Mediterranean Sea itself nearly dried up when tectonic movements closed its connection to the Atlantic Ocean. When that connection reopened, water from the Atlantic is believed to have rushed back into the basin in an event sometimes called the Zanclean Flood. Estimates suggest that this flood may have been one of the largest in Earth's history, filling the Mediterranean basin over a period that may have lasted months or years. The scale of that event is difficult to imagine, involving volumes of water far greater than those released from Lake Agassiz. Yet the underlying principle was similar. Water stored behind a barrier eventually found a path and moved rapidly downhill. Megafloods are not limited to Earth. Planetary scientists studying Mars have identified enormous channels that appear to have been carved by ancient floods. These channels, some hundreds of kilometers long, suggest that large volumes of water once flowed across the Martian surface. The sources of that water may have been underground reservoirs or ice deposits that melted or were suddenly released. The presence of such features on another planet highlights how universal these processes are. Wherever large amounts of water accumulate and natural barriers fail, floods of immense scale can occur. Returning to Earth, it is interesting to consider what these various floods have in common. In nearly every case, the key elements are the same: a large reservoir of water, a barrier that holds it in place, and conditions that weaken or breach that barrier. Once the water begins to flow, gravity and erosion do the rest. What differs from one event to another is the scale and the environment in which it occurs. Some floods carve channels through volcanic rock, others reshape sedimentary plains, and still others alter coastlines and ocean basins. Each leaves behind its own distinctive set of landforms, which scientists can study to reconstruct what happened. Comparing Lake Agassiz with other megafloods also helps put its magnitude into perspective. While it was not the largest flood in Earth's history, it was among the most significant in recent geological time, especially because of its potential influence on climate and human environments. Another aspect worth considering is how these floods often occur during periods of environmental change. The Missoula floods happened as glaciers were retreating at the end of the Ice Age. The drainage of Lake Agassiz occurred under similar conditions. Rising sea levels played a role in the flooding of the Black Sea basin. In each case, shifts in climate or tectonics created situations where large reservoirs of water formed and eventually drained. These patterns suggest that megafloods are part of the broader story of how Earth transitions between different climatic and geological states. They are not random events, but outcomes of processes that unfold over long periods, sometimes culminating in sudden releases of energy. For people living near such events, the experience would have been extraordinary, though the details are often lost to history. In some cases, floods may have influenced migration patterns or shaped cultural traditions, leaving echoes in myths or oral histories. While direct evidence is rare, it is easy to imagine how a sudden, overwhelming flood could leave a deep impression on those who witnessed it. The landscapes shaped by megafloods often remain striking long after the water is gone. Wide valleys, steep-sided channels, and fields of giant ripple marks serve as reminders of forces that once transformed the land in a short time. These features also provide natural laboratories where scientists can study erosion, sediment transport, and the dynamics of large flows. By comparing different megafloods, researchers gain a better understanding of the processes involved, improving models that can be applied to both past and present situations. This knowledge is useful not only for reconstructing ancient events, but also for assessing modern risks, such as the stability of glacial lakes in regions where warming temperatures are increasing the likelihood of outburst floods. There is something quietly humbling about recognizing how often water has reshaped the planet in ways that seem almost unimaginable when viewed from the perspective of everyday life. Rivers that normally move at a gentle pace can become torrents under the right conditions. Lakes that appear permanent can vanish in a matter of years. Entire basins can fill and empty, leaving behind landscapes that tell the story long after the water has gone. Lake Agassiz is part of that broader history, one example among many of how the interplay of ice, water and gravity can transform the surface of the Earth. By studying it alongside other megafloods, scientists have come to appreciate both the uniqueness of each event and the common processes that link them. Not everyone who lived near the margins of Lake Agassiz would have understood what was happening as the first signs of change appeared. Life near a great lake, even one of extraordinary size, would have followed rhythms that felt familiar. Water levels rose and fell slightly with the seasons. Shorelines shifted gradually. Winds came and went. To anyone living there, the lake might have seemed like a permanent feature of the world, as dependable as the horizon itself. Then, slowly at first, things would have begun to feel different. Rivers feeding the lake may have changed their behaviour. Currents near certain shorelines could have strengthened as water began to move toward an outlet that had not previously carried much flow. Along parts of the northern edge, distant sounds might have carried across the water, deep cracking noises from the glacier, or the low, continuous rumble of water forcing its way beneath the ice. Such sounds would not necessarily have caused alarm at first. Glaciers are noisy environments, ice shifts, cracks, and settles as it moves. But over time, those sounds might have become more frequent, more sustained, less like isolated events and more like something ongoing. Closer to the outlet where the drainage intensified, the change would have been unmistakable. Water that once flowed steadily through a channel would have begun to surge, rising higher along the banks, carrying debris, moving faster each day. The colour of the water might have shifted as sediments were stirred up, turning it cloudy and dense. Standing near such a channel would not have been peaceful. The sound alone would have been overwhelming, a deep, constant roar, punctuated by sharper crashes as ice broke or stones collided in the current. The ground might even have trembled faintly under the vibration of so much moving water. For people living farther from the outlet, the experience would have been different. The lake was so vast that its surface could not drop overnight in any noticeable way. Days might pass with only subtle changes. A shoreline that had once been close might gradually retreat, exposing damp sediments and stranded driftwood. Wetlands would shrink. Boats, if any were used, would need to be pulled farther to reach the water. Over weeks, the change would become clearer. The waterline would continue to move, revealing wide stretches of lake bed that had not seen daylight for centuries. The exposed ground would be soft at first, patterned with ripples left by waves, scattered with shells, stones, and the remains of aquatic plants. Birds and animals that depended on the water would begin to shift their behaviour. Some species might leave as the wetlands dried. Others would follow the retreating shoreline, feeding in newly exposed areas rich in stranded fish and invertebrates. The air near the lake might carry a different scent as well, the smell of wet sediment drying in the sun, mixed with the faint mineral odour of clay and silt. These are small details, but they are the kinds of things that make large changes perceptible to those living through them. Farther downstream, along the flood channels, the experience would have been far more dramatic. Water arriving there did not creep forward gently. It surged, filling valleys, overtopping banks, and sweeping away vegetation and soil. Anyone standing in the path of such a flood would have needed to move quickly to higher ground, though the speed of the rising water might have left little time. From a safe vantage point above the floodplain, the sight would have been extraordinary. Instead of a single river, the valley floor would have become a moving expanse of water stretching from one side to the other, its surface broken by waves, eddies, and floating debris. Entire trees, uprooted upstream, would drift past, turning slowly in the current. Blocks of ice carried from the glacier might grind against one another, cracking and rolling. The sound would have been continuous, a deep thunder of water moving at immense speed, louder than any storm or waterfall most people experience today. Even at a distance, it would dominate the landscape, echoing from valley walls and carrying for kilometres across open ground. Night would not have brought silence. The flood would continue in darkness, the roar of water replacing the usual quiet of evening. Reflections of moonlight on the surface might reveal the scale of the flow, a broad, shifting brightness where normally there would have been only a narrow ribbon of river. It is important to remember that such events did not necessarily unfold in a single day. The drainage of a lake the size of Agassiz likely continued for weeks or months, perhaps longer in some phases. For those witnessing it, the experience would have been one of sustained change rather than a single moment of catastrophe. The landscape itself would have transformed before their eyes. Channels would deepen, banks would collapse, and new pathways would open as water found routes of lower resistance. Areas that had once been forested might be stripped to bare sediment. Other regions would be buried beneath the layers of sand and silt deposited as the flood slowed. After the peak of the flood passed, the silence that followed might have felt almost unsettling. The roar of water would fade, replaced by the quieter sounds of wind and distant streams. The valleys would remain altered, their floors covered with fresh sediment, their shapes changed in ways that could not easily be reversed. For people returning to such areas, the land might have been difficult to recognise. Familiar landmarks would be gone, replaced by new channels, sandbars and wetlands. Paths once used for travel might be buried or cut off by new rivers, yet life has a way of returning even to disturbed landscapes. Within months or years, plants would begin to colonize the fresh sediments. Grasses and shrubs would take root, followed by trees in areas where soils developed more deeply. Animals would return, drawn by the new habitats created by the flood. The memory of the event, however, would linger in the minds of those who witnessed it. A flood of that scale would not be easily forgotten. Stories would likely have been told, passed from one generation to the next, though over thousands of years such stories would change, fade, or disappear entirely. Today, we do not have direct accounts of what it was like to see the waters of Lake Agassiz drain, but by studying the evidence left behind, the size of the channels, the distribution of sediments, the timing of climatic changes, we can form a grounded picture of how it must have appeared. This kind of reconstruction is not speculation in the sense of inventing events without evidence. It is an attempt to combine what we know about similar floods, modern glacial outburst events, and the physical traces in the landscape to imagine the experience in realistic terms. Modern glacial lake outburst floods, though much smaller, offer some clues. In regions such as Iceland or the Himalayas, sudden releases of water from ice-dammed lakes have produced torrents capable of destroying bridges, carving channels and reshaping valleys within hours. Observers describe a wall of water carrying ice and debris, accompanied by a roar that can be heard long before the flood arrives. Scaling such events up to the size of Lake Agassiz helps give a sense of the magnitude involved. The same processes were at work, only on a far larger scale. There's also a quieter side to imagining such moments. Not every observer would have been close to the most dramatic scenes. Many might simply have noticed the lake shrinking year by year, the shoreline retreating, new land appearing where water once stood. For them, the change would have felt gradual, almost ordinary, until they realized how much the world around them had altered. Standing on newly exposed ground, looking out across a lake that was smaller each season, they might not have known that the water they once saw stretching to the horizon was now flowing toward distant oceans, influencing climates far away. That contrast between the local experience and the global consequence is one of the most fascinating aspects of the story. To those living nearby, it was a changing landscape. To the planet as a whole, it was part of a chain of events affecting oceans and atmosphere. Thinking about this can bring a certain perspective. Many of the largest changes in Earth's history were not experienced as dramatic turning points by those who lived through them. They were experienced as shifts in weather, changes in rivers, gradual transformations of land and water. Only in hindsight, looking at the evidence across continents and centuries, does the full scale become clear. As the floodwaters of Lake Agassiz continued their journey, and the basin itself transformed into a network of smaller lakes and rivers, the world moved quietly into a new phase. The Ice Age was ending, climates were shifting, and landscapes were settling into forms that would persist into the present. Long after the floodwaters had moved on and the valleys began to quiet again, the effects of such an event did not simply disappear. Landscapes changed, climates shifted, and ecosystems adjusted, and all of those changes influenced the lives of the people who lived through that era. The connection between a megaflood and human history is not always direct or immediate, but it unfolds gradually through altered environments, new migration routes, and the changing availability of food and resources. To understand this connection, it helps to remember when these events occurred. The drainage of Lake Agassiz happened near the end of the last ice age, a time when human populations in North America were still relatively small and mobile. People lived as hunter-gatherers, moving across large territories in search of animals, edible plants, and materials for tools. Their survival depended closely on the landscape and climate around them. When the flood reshaped river valleys and exposed vast new plains where the lake had once stood, it created environments that would gradually become rich in vegetation. Fine sediments deposited in still water formed fertile soils, and as the climate warmed again after the Younger Dryas, grasses and other plants spread across these plains. Herds of grazing animals followed the new growth, and human groups likely followed the herds. In this way, an event that at first seemed destructive eventually contributed to landscapes that supported life in new ways. The flat, fertile plains of the former lake bed became corridors of movement for animals and people alike. Rivers established new courses across those plains, providing fresh water and guiding travel routes. Rivers have always played a central role in human history. They offer water, food, and natural pathways through the landscape. After the drainage of Lake Agassiz, the newly formed river systems would have shaped how people moved across the region, where they camped, and which routes became familiar over generations. Climate changes associated with the flood may also have influenced human societies more broadly. The Younger Dryas cooling altered vegetation patterns and animal distributions across large areas. In some regions, colder and drier conditions may have reduced the availability of certain food sources, encouraging people to adapt their diets, develop new tools, or move to different areas. Migration has always been one of humanity's most effective responses to environmental change. As glaciers retreated and new lands opened, people expanded into territories that had previously been covered by ice or dominated by cold climates. The end of the Ice Age was a time of exploration and movement, with groups gradually spreading into new regions of North America. Events like the drainage of Lake Agassiz would have influenced these movements by reshaping the terrain. Flooded valleys might have become barriers for a time, while newly exposed plains later became routes of travel. Wetlands formed in low-lying areas, attracting animals and providing resources that could support human communities. It is also possible that memories of large floods found their way into stories passed down through generations. Many cultures around the world have flood narratives in their traditions, though linking specific stories to specific events is difficult. Oral histories can preserve memories for long periods, but details often change and the original context may be lost. Still, it is easy to imagine how witnessing a flood of extraordinary scale could leave a lasting impression, shaping how people thought about rivers, lakes, and the forces of nature. Even if the exact events were not recorded in words that survive today, the experience itself would have influenced how communities understood their world. Another way such events shape human history is by influencing where future civilizations develop. Fertile soils left by ancient lakes and floods often become centers of agriculture once farming begins. Although agriculture did not appear in North America until thousands of years after Lake Agassiz drained, the rich soils of the former lake bed later supported farming communities and eventually modern cities. In this sense, the flood indirectly shaped patterns of settlement far in the future. Land that had once been underwater became productive farmland, capable of supporting large populations. Rivers that followed channels carved or enlarged by ancient floods continued to guide transportation and trade routes long after the event itself was forgotten. Looking beyond North America, similar patterns can be seen in other parts of the world. Many of the earliest agricultural civilizations developed in river valleys enriched by periodic flooding. The Nile, the Tigris and Euphrates, the Indus and the Yellow River all carried sediments that renewed soils and supported farming. Floods, while sometimes destructive, also created the conditions that allowed complex societies to emerge. The story of Lake Agassiz is different in scale and context, but it reflects the same principle. Water reshapes landscapes, and landscapes shape human lives. It is also worth considering how environmental changes influence technology and culture. When climates shift and resources change, people adapt. They develop new tools, new ways of hunting or gathering, and new strategies for surviving in unfamiliar conditions. Over long periods, these adaptations accumulate, contributing to cultural and technological evolution. The Younger Dryas cooling, for example, may have affected human populations not only in North America but also in Europe and the Near East. Some researchers suggest that climatic stress during this period encouraged experimentation with new food sources and eventually contributed to the development of agriculture in certain regions. While this process was complex and influenced by many factors, climate change was likely one of them. Returning to the landscapes shaped by Lake Agassiz, it is striking how the marks of the flood became part of the environment in which later generations lived. Valleys carved by ancient currents became river corridors. Sediments deposited by floodwaters formed soils. Wetlands and lakes created by the changing drainage patterns became habitats for animals and resources for people. From the perspective of someone living thousands of years later, these features would have seemed entirely natural, part of the landscape as it had always been. The connection to a long-vanished lake and its floods would not have been obvious. This reminds us that much of the environment we experience today has been shaped by events far older than any human memory. Mountains, valleys, plains, and coastlines all carry histories that extend far beyond recorded time. Understanding those histories helps us see the present landscape in a new way, as part of an ongoing process rather than a fixed stage. Events like the drainage of Lake Agassiz also offer lessons about the relationship between humans and the environment. They show how dependent people are on stable climates, reliable water sources, and predictable ecosystems. When those conditions change, societies must adapt, sometimes rapidly. In the modern world, where populations are much larger and infrastructure is more complex, environmental changes can have far-reaching consequences. Studying past events helps scientists understand how natural systems behave and how sensitive they can be to disturbances. There is also a quieter perspective to consider. For the people who lived near the shores of Lake Agassiz, the flood was not an abstract scientific event. It was part of their lived experience, shaping where they could travel, what they could eat, and how they understood the world around them. Their responses, whether moving to new territories or adapting to changing conditions, became part of the long story of human resilience. As centuries passed, the landscapes shaped by the flood became home to new generations who never knew the lake itself. Forests spread, rivers settled into stable channels, and animals returned to habitats that had been disturbed. Human communities continued to move and adapt, gradually shaping the land in their own ways. The influence of the flood faded into the background, yet it remained embedded in the geography, guiding rivers, defining soils, and shaping ecosystems that people depended on. In this way, the event continued to shape human history long after the last of its waters had reached the sea. Thinking about this connection between natural events and human lives invites reflection on how closely our own history is tied to the environment. Changes in climate, water, and land have always influenced where people live, how they travel, and what they eat. The story of Lake Agassiz is one chapter in that larger narrative, showing how even a single lake, under the right conditions, can play a role in shaping the course of life on Earth. Thinking about events as immense as the drainage of Lake Agassiz naturally leads to a quiet, lingering question. If it happened once, could something like it happen again? The world today is different in many ways from the one that existed at the end of the last ice age, yet the fundamental processes that shaped that flood, melting ice, accumulating water, and the sudden release of natural dams, have not disappeared. They are still part of how the planet works. To begin answering this question, it helps to consider what made Lake Agassiz possible in the first place. The key ingredients were a vast ice sheet, a landscape shaped in a way that trapped meltwater, and barriers of ice that blocked natural drainage routes. When temperatures rose and the ice weakened, the stored water eventually found pathways to escape. Today, continental ice sheets still exist, most notably in Greenland and Antarctica. These are the last great remnants of the massive ice sheets that once covered much of the northern hemisphere. They are enormous reservoirs of fresh water, holding enough ice to raise global sea level significantly if they were to melt entirely. However, the conditions surrounding them are not identical to those of the Ice Age, and large preglacial lakes on the scale of Agassiz are less common. That said, smaller glacial lakes do exist in many parts of the world, especially in regions where glaciers are retreating. In the Himalayas, the Andes, Alaska, and parts of Iceland, meltwater often collects behind natural dams made of ice or loose sediment. These lakes can grow rapidly as glaciers shrink, and in some cases the dams holding them in place fail, producing what are known as glacial lake outburst floods. These floods are much smaller than the megafloods of the past, but they can still be powerful enough to reshape valleys and threaten communities downstream. In recent decades, several such events have occurred, damaging infrastructure and altering river systems. Scientists and engineers now monitor many glacial lakes closely, watching for signs that water levels are rising or that dams are weakening. One reason such floods are more common today than in the recent past is the warming climate. As glaciers retreat more quickly, they often leave behind depressions that fill with meltwater. At the same time, the ice or sediment dams that hold these lakes in place may be unstable, especially if melting or erosion weakens them. In some regions, efforts have been made to reduce the risk by lowering lake levels or reinforcing natural dams. These measures are practical when lakes are relatively small, but they would not be feasible on the scale of something like Lake Agassiz. The sheer size of that ancient lake placed it far beyond any human ability to control. Another place where large volumes of fresh water are currently entering the ocean is Greenland. Each summer, meltwater flows across the surface of the ice sheet, forming rivers and lakes that sometimes drain suddenly through cracks in the ice. These events release large amounts of water over short periods, though still far less than the volumes associated with ancient megafloods. Scientists are studying how this fresh water affects the North Atlantic, particularly whether it might influence ocean circulation in ways similar to those inferred for the Younger Dryas. So far, any changes appear to be gradual rather than sudden, but the system is complex and researchers continue to monitor it carefully. Antarctica presents another set of possibilities. Beneath its ice sheet lie subglacial lakes, bodies of water trapped under kilometers of ice. These lakes can drain and refill over time, sometimes releasing water into the ocean beneath floating ice shelves. Most of these events are slow and relatively small in comparison to the floods associated with Lake Agassiz, but they demonstrate that large volumes of water can move beneath ice in ways that are not always visible at the surface. Sea level rise itself can also be thought of as a slow, ongoing flood, though one measured in millimeters per year rather than meters per day. As ice melts and oceans expand with warming temperatures, coastlines are gradually shifting. Low-lying areas are increasingly vulnerable to flooding, especially during storms. While this process lacks the drama of a sudden megaflood, its long-term impact on human societies may be just as significant. There is also the possibility, however remote, that large ice-dammed lakes could form again under the right conditions. In regions where glaciers still occupy mountain valleys, advancing ice could theoretically block drainage routes and allow water to accumulate. If the dam later failed, a large outburst flood could occur. Such scenarios are rare, but they are part of the natural behaviour of glaciers. Looking further back in time reminds us that the Earth's climate has changed many times, sometimes producing conditions very different from those we see today. During past glacial periods, large proglacial lakes were relatively common because ice sheets covered broad areas and blocked natural drainage pathways. If another major glaciation were to occur in the distant future, similar lakes could form again. From the perspective of human timescales, however, the return of continental ice sheets like those of the Ice Age is unlikely in the near future. Current climate trends point toward continued warming rather than cooling, meaning that the processes most relevant today involve melting ice and rising seas, rather than advancing glaciers. Still, studying ancient floods like the one from Lake Agassiz remains important, because it helps scientists understand how large volumes of fresh water can influence ocean circulation and climate. These insights are valuable for predicting how modern changes might unfold. Another lesson from the past is how landscapes respond to sudden changes. Flood channels, sediment deposits, and altered river systems all show that water can reshape the land quickly under the right conditions. This understanding informs modern efforts to manage rivers, design dams, and prepare for extreme weather events. It is also worth reflecting on how our perception of time shapes the way we think about such events. A flood lasting weeks or months may seem brief compared to the centuries it took for Lake Agassiz to form, yet its effects lasted thousands of years. In the same way, changes occurring today, even if gradual, may have consequences that extend far into the future. Thinking about whether something like the Lake Agassiz flood could happen again also invites a broader perspective. The exact circumstances that created that lake were unique to a particular moment in Earth's history, but the underlying processes, the storage of water, the weakening of barriers, and the sudden release of energy are universal. They occur in different forms in rivers, glaciers, volcanoes, and even the atmosphere. Nature does not repeat events in exactly the same way, but it often follows patterns. Understanding those patterns allows us to recognize risks, interpret evidence, and appreciate the dynamic character of the planet. There is a certain calmness in recognizing that the Earth has always been a place of change. Landscapes evolve, climates shift, and water moves through cycles that connect mountains, plains, and oceans. The flood from Lake Agassiz was one expression of that ongoing movement, dramatic in its scale, but part of a larger story that continues today. Long after the last strong currents had faded and the immense lake had broken apart into smaller waters, the land entered a period of stillness that must have felt almost unfamiliar. Valleys that had carried torrents were quiet again. Newly exposed plains lay open beneath the sky, their surfaces damp in places, drying in others, marked by faint ripples and scattered stones left behind by retreating water. The transformation had been dramatic while it lasted, yet what followed was not another sudden change, but a gradual settling, the kind of slow adjustment that the Earth carries out over years, decades, and centuries. Rivers began to find stable paths through the sediments left behind. At first, their channels would have shifted often, cutting through soft ground, dividing and rejoining as they searched for routes of least resistance. Over time, those channels deepened and steadied, guided by gravity and the shape of the land. What had once been temporary streams flowing across a vast lake bed became the permanent rivers of a new landscape. Vegetation returned in stages. The first plants to take root were likely hardy grasses and small, fast-growing species capable of colonizing bare sediment. Their roots held the soil in place, reducing erosion and creating conditions where other plants could grow. Shrubs followed, and eventually trees in areas where the climate allowed. What had been an expanse of water only centuries before gradually became a patchwork of meadows, wetlands, and forests. Animals moved into these changing environments as well. Insects appeared among the plants, birds arrived to feed and nest, and grazing animals followed the spread of vegetation. Predators followed the grazers. Life, which had retreated or shifted during the time of the lake and the flood, adapted once again to the new conditions. For the people living in the region, the changes would have unfolded slowly enough to feel almost natural. A shoreline that once lay at a certain place would no longer be there. A river that once emptied into a vast body of water would now continue across open land. Wetlands might appear where none had existed before. Over the span of a human lifetime, the differences might have seemed modest, yet over generations the landscape would have been transformed. There is something quietly remarkable about how quickly ecosystems can begin to recover after even the most dramatic disturbances. Sediments deposited by floods are often rich in minerals, and once stabilized by plants, they can support abundant life. In this way, the aftermath of destruction becomes the foundation for renewal. The plains left behind by Lake Agassiz eventually became some of the most fertile lands in North America. The same fine sediments that once settled slowly through still water now form soils capable of supporting crops, grasses and forests. Fields that stretch to the horizon today owe their productivity to processes that began thousands of years ago, when glacial meltwater carried particles of rock into a vast inland sea. Looking across such a plain today, it is difficult to imagine that it was once covered by water deep enough to float icebergs. The surface seems permanent and unchanging, yet beneath the soil lie layers of clay and silt that preserve a quiet record of that earlier time. The rivers that now cross those plains also carry the memory of the flood. Many follow valleys carved or enlarged by ancient currents. Their courses were guided long ago by water moving in volumes far greater than anything seen today. The rivers themselves are smaller now, quieter, yet they remain part of a system shaped by events thousands of years in the past. This continuity between past and present is one of the most striking aspects of geology. The landscapes we see today are not separate from history, they are the result of it. Every valley, every plain, every shoreline has been shaped by processes that may still be ongoing or may have ended long ago. It is easy to think of time in human terms, measured in years or decades, but the Earth works on different scales. A flood lasting weeks can leave marks that persist for tens of thousands of years. A glacier advancing over centuries can reshape an entire continent. The quiet period after such events may last longer than the events themselves, yet it is during those quieter times that the foundations of future landscapes are laid. There is also a certain calmness in recognizing how patient these processes are. The land does not hurry. Rivers carve their channels grain by grain. Plants spread one generation at a time. Soils develop slowly as organic material accumulates and minerals weather. The quiet after the waters is not empty or inactive. It is filled with gradual change. Climate, too, continued to shift after the floods ended. The Younger Dryas cooling eventually gave way to warmer conditions, and the planet moved further into the interglacial period that continues today. Ice sheets retreated farther north, sea levels rose, and ecosystems expanded into newly available regions. These changes influenced human societies in ways both subtle and profound. As climate stabilized and environments became more predictable, opportunities for new ways of living emerged. Over thousands of years, agriculture developed in some parts of the world, settlements grew, and civilizations formed. The events surrounding Lake Agassiz were only one small part of this broader transformation, yet they were connected to the same processes shaping the planet at that time. Thinking about these connections can bring a sense of perspective. The flood itself was dramatic, but it was also part of a continuum of change that stretches far beyond any single event. Before the lake formed, glaciers had advanced and retreated many times. After it drained, rivers and forests continued to evolve. The Earth is always in motion, even when the changes are too slow to notice from day to day. Standing in a quiet landscape today, it is possible to feel that sense of stillness, yet beneath it lies a history of movement and transformation. The ground beneath your feet may once have been the floor of a lake, the bed of a river, or the path of a glacier. Over long periods, water, ice, and wind have reshaped every part of the surface. There is also something comforting in this continuity. The same processes that shaped the past are still at work today, though often at a gentler pace. Rain falls, rivers flow, sediments settle, and plants grow. Change continues, but not always in ways that are dramatic or sudden. Reflecting on the story of Lake Agassiz invites a broader appreciation of water itself. Water is one of the most common substances on Earth, yet it is also one of the most powerful agents of change. It can wear down mountains, carve valleys, transport nutrients, and support life in countless forms. In large quantities, it can reshape continents and influence climate. In small quantities, it sustains every living organism. The same element that falls quietly as rain, or rests peacefully in a pond can, under certain conditions, become a force capable of altering the course of history. This dual nature, gentle and powerful, ordinary and extraordinary, is part of what makes water so fascinating to study. Another thought worth considering is how much of Earth's history is recorded not in written words, but in physical traces. Sediment layers, fossil shells, ancient shorelines and carved valleys are all forms of memory. They preserve information about events that occurred long before humans could record them. By learning to read these traces, scientists have been able to reconstruct stories like that of Lake Agassiz. Each layer of clay, each ridge of sand, each channel cut into bedrock adds a piece to the puzzle. The process requires patience and careful observation, but the reward is a deeper understanding of how the planet works. This understanding also helps us see our own place in a wider context. Human history, long as it may seem, occupies only a small fraction of Earth's timeline. Civilizations rise and fall, languages change and cultures evolve, all within a period that is brief compared to the ages of glaciers and oceans. Yet this does not make human history insignificant. On the contrary, it highlights how remarkable it is that we can study events so far in the past and piece together their stories. The ability to look at a valley or a sediment core and understand something about what happened thousands of years ago is one of the quiet achievements of science. There is also a gentle reminder in these stories about the importance of paying attention to the world around us. Landscapes are not just scenery, they are records of change. Rivers, lakes and coastlines are not fixed, they are part of ongoing processes. Recognizing this can deepen our sense of connection to the planet. As the last remnants of Lake Agassiz disappeared and the land settled into its new form, the world moved on, as it always does. Seasons followed one another, forests expanded and contracted, rivers shifted slightly within their valleys. The traces of the flood remained, but they became part of the background, features of the landscape rather than signs of a recent event. Thousands of years later, people would stand in those same places, unaware that beneath the soil lay the sediments of an ancient lake, or that the broad valley nearby had once carried a torrent greater than any river now flowing there. Only careful study would reveal the story hidden in the land, and so the quiet after the waters is not an ending in the usual sense. It is simply another phase in the long history of a changing planet. The flood passed, the land recovered, life adapted, and the processes of erosion, deposition and growth continued, just as they had before, and just as they will continue in the future. If you picture the landscape now, long after the events we have been talking about, it is peaceful. Wind moves through grasses, a river flows steadily in its channel, the sky reflects in small lakes that remain where the Great Lake once stood. Nothing in that calm scene suggests the scale of what happened long ago, yet the evidence is there for those who look closely. And perhaps that is one of the most soothing ideas to carry with you. The Earth changes, sometimes dramatically, sometimes slowly, yet after each transformation comes a period of quiet, a time when rivers settle, plants grow, and the world finds a new balance. With that thought, you can let the image of those quiet plains and steady rivers linger, the memory of the waters that once moved like a continent fading gently into the background, leaving only the calm rhythm of wind, water, and time continuing on, just as they always have.